In the farthest reaches of the universe, there exists a strange and terrifying phenomenon: black holes. These cosmic entities are so dense that not even light can escape their grasp, bending the fabric of space and time beyond recognition. They represent the ultimate unknown, where the rules of physics collapse, and reality is no longer what we understand it to be. But what if everything we know, everything we observe in the universe, is actually contained within one of these enigmatic voids? Could we be living inside a black hole? The James Webb Space Telescope has recently revealed discoveries that challenge everything we thought we knew about space and time. It has shown us patterns that should be impossible if our universe were truly random. Some scientists even speculate that our universe might be a black hole, an observation-defying object with its own event horizon, singularity, and complex gravitational dynamics. In this journey, we will delve into the idea of whether humanity could ever reach a black hole, or if it is simply beyond our technological capabilities. What would it take to approach such an enigmatic object, and is it even possible to survive the experience? From exploring the nature of black holes to understanding the science behind them, we will investigate the immense barriers that stand between us and these cosmic monsters. Are black holes merely objects of theoretical curiosity, or could they hold the key to understanding the deeper structure of our universe? As we embark on this cosmic journey, we'll unravel the mystery, asking whether we can truly reach a black hole, or if it's simply a dream too far for humanity to achieve. Chapter 1. What is a black hole? A black hole is one of the most mysterious and extreme objects in the universe, a place where the laws of physics as we know them begin to crumble. At its core, a black hole is defined by an intense gravitational pull that nothing, not even light, can escape. To understand black holes, we need to first explore the key components that make them so unique: the event horizon, the singularity, and the mass that defines them. A black hole is born when a massive star reaches the end of its life cycle. Stars, particularly those much more massive than our Sun, go through a process of nuclear fusion to keep their inner pressure balanced against gravity. This balance prevents the star from collapsing under its own weight. However, once the star has exhausted its nuclear fuel, it can no longer maintain this balance. The result is a catastrophic collapse under its own gravity. The outer layers of the star are ejected in a violent explosion known as a supernova, while the core condenses into an incredibly dense object, often forming a black hole. The defining feature of a black hole is its gravitational pull. The mass of the collapsing star determines the mass of the resulting black hole, and this mass directly affects the size of the black hole's event horizon. The event horizon is the boundary around the black hole where the escape velocity exceeds the speed of light. This means that nothing, not even light, can escape from within this boundary. Once anything crosses the event horizon, it is doomed to fall inward toward the singularity at the center of the black hole, where all the mass is concentrated into a point of infinite density. The singularity is a concept that is incredibly difficult to comprehend. It is a point where space and time break down completely, and the laws of physics no longer function in ways we understand. At this point, matter is crushed to an infinite density, and space-time is warped beyond recognition. The singularity defies classical physics, especially general relativity, which predicts its existence, but fails to explain what happens inside. It's a region where all our current models of physics fall short, and this is part of what makes black holes so baffling. The event horizon marks the point of no return. Once an object passes this boundary, it is irretrievably pulled toward the singularity. To the outside observer, time appears to slow down as the object approaches the event horizon. From their perspective, the object would seem to freeze in time, gradually fading away as it crosses the boundary, never quite reaching it. However, from the perspective of the object itself, it would experience no such time dilation. It would continue falling inward, unaware of any external time distortions, until it reaches the singularity. While the concept of black holes seems abstract, their formation and properties can be traced back to basic physics principles. The mass of a star plays a pivotal role in determining whether it will end its life as a white dwarf, a neutron star, or a black hole. A star with sufficient mass, usually greater than 8 times that of the Sun, will undergo a collapse that leads to the creation of a black hole. As the core of the star collapses, it compresses all of its matter into an incredibly small space. This compression leads to the creation of the event horizon, and thus the formation of a black hole. What makes black holes so difficult to understand is the fact that they challenge the boundaries of human knowledge. The equations of general relativity predict the existence of black holes, yet they also suggest that at the heart of a black hole lies a singularity, where the very fabric of space and time breaks down. This creates a paradox. We can calculate and measure the properties of black holes based on the effects they have on their surroundings, but we can never observe what happens inside. The interior of a black hole is completely inaccessible to us, hidden behind the event horizon. Scientists have proposed several theories to explain what might happen inside a black hole, but none of them are conclusive. One of the most intriguing aspects of black holes is that they can teach us about the nature of gravity and the limits of physics. The immense gravitational forces near a black hole cause space and time to curve in ways that we cannot fully model with our current understanding. The closer an object gets to the event horizon, the more extreme the warping of space-time becomes, until at the singularity, time and space cease to have meaning. Despite the many mysteries surrounding black holes, they are not just theoretical objects. Evidence for their existence has been observed in several ways. One of the most significant pieces of evidence comes from the discovery of gravitational waves, ripples in space-time caused by the acceleration of massive objects. In 2015, scientists detected gravitational waves from the collision of 2 black holes, providing direct evidence that black holes exist and that they can merge to form even larger black holes. Additionally, the Event Horizon Telescope has managed to capture the first ever image of a black hole's event horizon, offering us a glimpse of these otherwise invisible giants. The fact that black holes are so far beyond our everyday experience makes them both awe-inspiring and perplexing. They are not just points of interest for astronomers, they also pose profound questions about the nature of space, time, and the universe itself. Their extreme properties force us to confront the limits of our understanding of physics, and they raise the possibility that there are fundamental aspects of the universe we may never be able to comprehend fully. The study of black holes pushes the boundaries of science and challenges our perceptions of reality. Understanding black holes is not just about knowing what they are, it's about exploring the deeper implications of their existence. They force us to rethink the nature of time, the possibility of alternate realities, and the limits of human knowledge. As we continue to study these cosmic monsters, we may uncover insights that fundamentally change our understanding of the universe and our place within it. Chapter 2: The Size and Scale of Black Holes. Black holes are as fascinating as they are enigmatic. While they remain invisible in the conventional sense, their immense influence on the surrounding universe makes them both awe-inspiring and terrifying. But how big are they? How do their mass and size relate to each other? And just how does a single object in space become so massive that not even light can escape its pull? To understand the size of black holes, it's important to start with the concept of mass. A black hole's mass plays a crucial role in determining its size. Black holes, unlike everyday objects, are not restricted by the usual laws of physics when it comes to size. The more mass a black hole has, the larger its event horizon, which is the boundary beyond which nothing can escape. And this relationship is linear. Double the mass of a black hole, and you double the size of its event horizon. The event horizon is an essential feature of black holes. It marks the point of no return, a spherical boundary surrounding the black hole where escape becomes impossible. The size of this boundary is directly proportional to the mass of the black hole. For example, a stellar mass black hole, which forms from the collapse of a massive star, will have an event horizon just a few kilometers across. In contrast, a supermassive black hole, which can weigh millions to billions of times more than the Sun, can have an event horizon that spans several million kilometres. But the size of black holes is not just a matter of scaling mass up and down. Black holes can range vastly in size, with different categories based on their mass. At one end of the spectrum are stellar mass black holes, formed from the collapse of a star at the end of its life cycle. These black holes typically have masses between 3 and 10 times that of the Sun, and their event horizons are relatively small, ranging from a few kilometres to tens of kilometres in diameter. While they are relatively small by cosmic standards, stellar mass black holes still exhibit intense gravitational effects and are capable of significantly altering their surroundings. At the other end of the spectrum are supermassive black holes, which reside at the centres of most galaxies, including our own Milky Way. These giants can have masses that range from millions to billions of times the mass of our Sun, and their event horizons can span millions of kilometres. In fact, the supermassive black hole at the centre of our galaxy, Sagittarius A star, has a mass of about 4 million solar masses, and its event horizon is about 44 million kilometres across. These supermassive black holes play a pivotal role in galaxy formation and evolution, and they are believed to have been present at the very beginning of the universe, growing alongside the galaxies they inhabit. One of the most interesting aspects of black holes is that their size is not limited by their mass. Theoretically, the size of a black hole can grow indefinitely, given enough mass. The largest known black holes, often referred to as ultramassive black holes, can weigh tens of billions of solar masses and can have event horizons spanning up to several billion kilometres. These black holes are typically found in the centres of massive galaxies, where they have likely been accumulating matter over billions of years. However, even the largest black holes we know of are still just a fraction of the size of the universe itself. This vast difference in scale highlights the incomprehensible nature of black holes, as they can be incredibly dense, yet their size in comparison to the cosmos is minuscule. When we look at the scale of the universe, it becomes clear just how small even the largest black holes are in the grand scheme of things. The observable universe stretches across about 93 billion light-years. When we consider that the largest known black holes are only a few billion kilometres across, the contrast is staggering. Even the largest supermassive black holes, with their event horizons millions of kilometres wide, are just tiny specks in the vastness of the cosmos. Yet, despite their relatively small size compared to the universe, black holes exert an immense influence. Their gravitational pull distorts space and time, bending light and warping the fabric of the universe itself. They can suck in entire stars, and in some cases, they may even be able to devour whole galaxies. The presence of a black hole can dramatically affect the shape and behaviour of a galaxy, influencing the orbits of stars and shaping the overall structure of the galaxy. Supermassive black holes are believed to play a central role in the formation and evolution of galaxies, driving the flow of gas and dust, and regulating star formation. They are not only cosmic giants in their own right, but also the engines that power many of the most energetic phenomena we observe in the universe. The size and scale of black holes also tie into their ability to shape the universe. As mass accumulates and black holes grow larger, they influence the surrounding space in increasingly dramatic ways. For instance, when a black hole's mass reaches a certain threshold, it can begin to influence its environment with such force that it triggers the formation of new stars. This phenomenon, known as black hole feedback, can have far-reaching consequences for the surrounding galaxies, regulating star formation and shaping the overall structure of the universe. One of the most intriguing aspects of black holes is how their size and scale give us clues about the history of the universe itself. Because supermassive black holes are thought to be present at the centres of most galaxies, and many are found in ancient galaxies that formed early in the universe's history. Studying these black holes can provide insight into the early stages of galaxy formation. Some of the most distant black holes we observe today are thought to have formed only a few 100 million years after the Big Bang, offering us a glimpse into the formation of the very first galaxies. But while we've made significant strides in observing and studying black holes, the true nature of their size and scale remains elusive. Our understanding of these cosmic giants is still in its infancy, and much of what we know comes from mathematical models and indirect observations. Black holes remain in many ways the ultimate cosmic mystery, pushing the boundaries of our understanding of the universe. Their size and scale are but a glimpse into the mind-bending complexity of the cosmos, and the more we learn about them, the more we realize how much we still have to discover. Chapter 3: The Black Hole's Event. Horizon, no return. The event horizon is one of the most enigmatic features of black holes. It is the defining characteristic that separates black holes from all other objects in space. The event horizon marks the point of no return, a boundary in space where the gravitational pull of the black hole becomes so intense that even light, the fastest thing in the universe, cannot escape. Once something crosses this line, it is trapped forever, unable to escape the black hole's grasp. To understand the event horizon, we first need to comprehend the nature of a black hole. A black hole is an object with an incredibly strong gravitational pull, so strong that not even light can escape from it. The reason for this is that the escape velocity from a black hole's surface exceeds the speed of light. This is why black holes appear black. No light can escape to reach our eyes. The event horizon is not a physical surface, but rather a mathematical boundary. It is the point beyond which nothing, no matter, no radiation, can escape the black hole's gravitational influence. One of the most fascinating aspects of the event horizon is its relationship with time. As you approach the event horizon, the effects of time dilation become increasingly pronounced. According to Einstein's theory of relativity, as you get closer to the event horizon, time appears to slow down. For an observer watching someone fall into a black hole, it would seem as though the person approaching the event horizon is moving slower and slower, almost freezing in place at the event horizon. To the person falling in, however, time would appear to pass normally, although they would experience a very different reality. The event horizon is not just a place where things get stuck. The immense gravity of a black hole also causes what is known as spaghettification. As you approach the event horizon, the difference in gravity between your feet and your head becomes so intense that the body is stretched out lengthwise and compressed in width. This process is known as tidal stretching, and it would result in the complete disintegration of anything that gets too close. It's a violent and inescapable fate that renders the journey through a black hole's event horizon lethal. So, what exactly happens when an object crosses the event horizon? According to classical physics, the object would be drawn inexorably toward the singularity at the center of the black hole, where gravity becomes infinitely strong, and the laws of physics as we know them break down. The singularity represents a point where the curvature of space-time is infinite, and all known theories of physics fail to describe the conditions. The singularity is often referred to as the point of no return, because any object that reaches this point is crushed to infinite density. However, because no information can escape a black hole, we cannot directly observe what happens inside it. Our understanding is, therefore, based on theoretical models that predict extreme conditions inside the event horizon, but we cannot confirm them through direct observation. The event horizon serves as a boundary not only for matter, but also for information. The information paradox is a major unresolved problem in theoretical physics. According to quantum mechanics, information cannot be destroyed. Yet once an object crosses the event horizon, the information about its properties, such as its mass, charge, and angular momentum, seems to be lost forever. This contradiction between quantum mechanics and general relativity, known as the black hole information paradox, has led to numerous debates among physicists. Some have suggested that the information is encoded on the event horizon itself, while others have speculated that black holes might eventually evaporate through a process known as Hawking radiation, which would allow the information to be released back into the universe. While the event horizon is the point beyond which nothing can escape, it's important to note that the event horizon itself is not a solid surface. It is simply a region where the escape velocity reaches the speed of light. In fact, if you were to hover right at the event horizon, you would not immediately notice anything unusual. However, the closer you get to the singularity, the stronger the tidal forces become, and the greater the risk of being spaghettified. The event horizon is not an impenetrable barrier, but rather a threshold that separates the known universe from the unknown. Once you cross it, you enter a realm where conventional physics ceases to operate in the way we understand. The concept of the event horizon challenges our understanding of the nature of space-time. It forces us to confront the reality that the universe may not be as open and accessible as we once thought. It raises profound questions about the limits of human exploration and whether we can ever truly understand what happens inside a black hole. While the event horizon remains a fascinating object of study, its very nature suggests that some aspects of the universe may forever remain beyond our reach. In summary, the event horizon of a black hole is a boundary beyond which nothing can escape, not even light. It marks the point of no return, where space-time becomes so warped that gravity dominates every aspect of the environment. As objects approach this boundary, they are subject to extreme tidal forces, and their very essence is torn apart by the immense gravity. Though it may seem like a cosmic prison, the event horizon is not just an obstacle, but a window into the unknown, forcing us to question the limits of space, time, and even reality itself. Chapter 4. The concept of falling into a black hole. Falling into a black hole, an experience that only exists in the realm of theoretical physics, presents a range of mind-bending phenomena. To imagine this, we need to strip away our usual conceptions of gravity, space, and time, and explore what would happen when you fall into one of these cosmic giants. The journey into a black hole is far more complicated than simply crossing the event horizon. It involves profound alterations to the very fabric of space-time, and no physical experience could ever fully prepare you for the bizarre and lethal environment inside. As you approach a black hole, you would first notice the effects of increasing gravitational forces. This isn't just the usual sensation of gravity we feel on Earth. The forces you'd experience near a black hole are extreme and dangerous. The closer you get to the event horizon, the more pronounced the difference becomes between the gravitational pull at your feet and the pull at your head. This difference, called tidal forces, increases as you get closer to the black hole. Imagine your body being stretched out like spaghetti, a phenomenon called spaghettification. This stretching occurs because the gravitational pull at your feet is stronger than at your head, and as you continue to approach the event horizon, this gradient becomes extreme. For a person falling into a stellar mass black hole, the tidal forces would become so strong that they would eventually tear your body apart long before you reach the singularity. This leads to an important question. Would it be possible to survive the journey into a black hole? According to the current understanding of physics, the answer is a resounding no. Once you cross the event horizon, the forces at play become so intense that no matter how resilient the human body is, there is no way to survive. But even before reaching the event horizon, the experience is nothing short of strange. As you fall toward the black hole, time would appear to slow down, at least from the perspective of an outside observer. To someone watching you fall in, it would seem as if you were slowing down and never quite reaching the event horizon, frozen in space-time. But for you, as the individual falling, time would appear to pass normally. You wouldn't notice the strange effects of time dilation yourself, except perhaps for the way the black hole begins to stretch and distort the light around you. At some point, you would cross the event horizon, the threshold from which nothing can escape. But inside the event horizon, the experience of falling into the black hole would be less clear. If you were able to observe your surroundings, you would witness the universe collapsing into an ever-shrinking point as you continued to approach the singularity. The intense gravitational forces distort space-time, pulling the universe in on itself. But as you get closer to the singularity, the very nature of time begins to break down. The standard understanding of physics begins to dissolve as well. The closer you get to the singularity, the more space-time becomes so warped that there is no longer a clear distinction between time and space. The mathematical models we use to describe the universe simply fail to provide us with any reliable predictions for what happens beyond this point. It is here, in the core of the black hole, that the laws of physics, as we know them, stop being useful. This brings us to one of the biggest mysteries of black holes. What actually happens at the singularity, the point at the very center of the black hole, where all the matter and energy collapse into an infinitely small and dense point? Theories about the singularity vary, but one thing is clear. It's a place where the traditional laws of physics no longer apply. Einstein's general theory of relativity, which governs our understanding of gravity, predicts that the singularity is a point where the curvature of space-time becomes infinite. In other words, space-time becomes so warped that it collapses in on itself. What happens inside this point is still unknown, and many scientists believe that understanding black holes and the singularity will require a new theory, one that combines general relativity with quantum mechanics. But even beyond the singularity, there are a number of peculiarities that await those who venture toward this cosmic abyss. As you continue to fall deeper, you would experience what's known as gravitational time dilation. According to general relativity, the closer you get to a massive object like a black hole, the slower time appears to pass for you, relative to an outside observer. To someone watching from afar, you would appear to be slowing down as you fall toward the event horizon, and eventually you would seem to freeze in place. This is a result of the distortion of time itself. However, from your perspective, time would continue as it always had. You would feel as if you were falling normally, though you would not be able to perceive the time distortion happening outside of your experience. As you approach the singularity, space itself would warp too. The familiar dimensions of space would bend and distort as the gravitational pull of the black hole becomes stronger. The way we perceive distance and orientation in space would be completely altered by the time you reach the event horizon. You would be traveling through a region of space-time that no longer operates under the familiar laws of the universe. You would be witnessing the very fabric of space itself tearing and stretching under the extreme forces of the black hole. There's also the concept of what happens to light around a black hole, which leads to the intriguing question: could we ever see into the heart of a black hole? The answer is more complicated than you might think. Black holes distort light so drastically that it bends and twists around them, making it impossible for us to observe what is going on inside. Light gets trapped in the gravitational pull of the black hole and cannot escape, meaning that the interior of a black hole is completely hidden from view. All we can observe is the light that bends around the black hole's event horizon, revealing only a small portion of the surrounding space. Given all of these factors, spaghettification, time dilation, and the sheer impossibility of knowing what happens at the singularity, the question arises: can we ever truly fall into a black hole? Theoretically, we can explore the black hole's vicinity and observe its effects on nearby stars and space-time, but we cannot physically reach the singularity. We are unable to know with certainty what lies beyond the event horizon, and what happens to matter and energy once it falls into a black hole remains one of the greatest mysteries of modern science. The idea of falling into a black hole might seem fantastical, and indeed it's an event that can only exist in theoretical physics. Still, these concepts force us to rethink our understanding of space, time, and the fundamental laws that govern the universe. As we continue to explore black holes and other cosmic mysteries, we will likely encounter even more unexpected phenomena, forcing us to expand our understanding of reality itself. The journey toward understanding black holes is as mysterious as the objects themselves. Chapter 5: The Limitations of Current Technology. When we look up at the night sky and consider the stars, planets, and the many wonders of the universe, it's easy to imagine that one day humanity will conquer space in ways that are beyond our wildest dreams. But as we dream of black holes, interstellar travel, and far-flung galaxies, the limitations of current technology quickly become apparent. Our most advanced spacecraft, such as the Voyager and New Horizons probes, have pushed the boundaries of human exploration beyond our solar system. Yet their speeds remain laughably slow when compared to the vast distances involved in reaching even the closest stars, let alone a black hole. At present, the fastest spacecraft humanity has ever built is the Parker Solar Probe, which can reach speeds of about 700,000 kilometers per hour. While this is mind-bogglingly fast compared to anything we've ever experienced on Earth, it still falls vastly short of what would be required to even approach a black hole. The nearest known black hole, V616 Monocerotis, is located about 3,000 light-years away, while the supermassive black hole at the centre of our galaxy, Sagittarius A star, is over 25,000 light-years away. To reach either of these, we would need to travel at a speed far greater than what our current technology can achieve. Even if we could use the Parker Solar Probe's top speed to travel to V616 Monocerotis, the journey would take over 4,000 years. To reach Sagittarius A star, we would be looking at a trip lasting over 200,000 years. These distances alone make it abundantly clear that our current propulsion systems are not up to the task of exploring these cosmic giants, let alone one as far away as a black hole. This presents the first and most glaring limitation when it comes to reaching black holes: time. No human civilization could survive such a journey, and no machine built today could endure the span of time necessary to complete it. In addition to the time factor, there's the issue of energy. Space travel requires an immense amount of power, especially when you're dealing with the massive distances involved in interstellar travel. The energy required to propel even a small spacecraft to a significant fraction of the speed of light is astronomical, and our current energy sources simply cannot provide that kind of power. If we were to rely on chemical propulsion, we would need an unimaginable amount of fuel, and the further we try to go, the more fuel we would need. Currently, we have no feasible way to generate enough energy for a meaningful interstellar journey. The issue of energy also ties directly into the propulsion systems we use. Most of the spacecraft we have sent out into the cosmos rely on chemical propulsion, which is incredibly inefficient when you think about the immense distances that need to be covered. The New Horizons spacecraft, for instance, used a gravity assist from Jupiter to gain speed on its journey to Pluto. While these gravity assists are incredibly useful for gaining speed without needing to carry as much fuel, they are still highly limited by the paths and objects we can align with in space. To actually make meaningful progress toward a black hole, we would need a propulsion system that can provide consistent thrust over an incredibly long period. Nuclear propulsion has been proposed as one potential solution to this problem, and it is far more efficient than chemical propulsion. The idea of using nuclear fission or fusion as a power source could, in theory, provide the necessary energy to get a spacecraft moving faster over long distances. However, we are still far from being able to create such propulsion systems that are reliable and capable of providing the thrust necessary for interstellar travel. While there have been experiments with nuclear thermal rockets, we still lack the technology to harness nuclear fusion for propulsion. Furthermore, these systems would still require significant advancements in energy generation, efficiency, and heat management. The development of antimatter propulsion systems, which would use the energy released from the annihilation of matter and antimatter, has also been proposed as a solution. Antimatter propulsion has the theoretical potential to be incredibly efficient, but antimatter is still only produced in minuscule quantities, and the technology required to store and safely use antimatter is decades away from being realized. Even if we could manufacture enough antimatter to use it as a propulsion fuel, the amount of energy required to make it would be so vast that we would need to develop new energy generation technologies just to power the antimatter production process itself. One of the more outlandish but exciting theoretical proposals is the concept of laser propulsion. as envisioned by the Breakthrough Starshot Initiative. The idea behind laser propulsion is to use powerful ground-based lasers to fire photons at a small, lightweight spacecraft equipped with a sail. These photons would carry momentum, gradually accelerating the spacecraft to a significant fraction of the speed of light. If successful, this method could drastically reduce travel times, potentially allowing humanity to reach the closest stars in just a few decades. However, as promising as this concept sounds, it faces numerous technical challenges. For instance, the precision required to keep the laser focused on the tiny spacecraft over interstellar distances is beyond our current capabilities, and the amount of energy needed to accelerate a spacecraft to these speeds would require unprecedented infrastructure and resources. At present, the prospect of reaching a black hole remains firmly in the realm of science fiction. The limitations of our technology are simply too great to overcome with the propulsion systems we have today. Even with promising future technologies, the energy requirements, timescales, and distances involved in interstellar travel are so vast that the challenge seems insurmountable. We are left with the paradox of exploring the unreachable, constantly refining our technology and pushing the boundaries of what is possible, yet unable to make the kind of advancements that would allow us to reach these distant cosmic objects. In the end, our exploration of black holes and the possibility of reaching them is an exercise in understanding our own limitations, as much as it is about exploring the vastness of the universe. With our current technology, black holes are as distant as ever, and the goal of traveling to one is an impossibility that challenges our understanding of space, time, and the very nature of existence. Yet it is this very pursuit of knowledge that drives us forward, pushing the boundaries of exploration, as we seek to understand the mysteries of the universe, even if we may never reach them. Chapter 6: The Impossibility of Reaching a Black Hole. When we talk about the distances separating us from black holes, the sheer scale is almost incomprehensible. Even the closest black hole to Earth, V616 Monachorotis, is still located 3,000 light-years away, which at first glance doesn't seem too far in astronomical terms. But as we delve deeper into the numbers and the practical realities of interstellar travel, the magnitude of the challenge becomes clear. A light-year, the distance light travels in 1 year, is about 9.46 trillion kilometers. Multiply that by 3,000, and you get roughly 28.4 quadrillion kilometers. That's an unimaginable distance, far beyond the reach of any spacecraft humanity has ever built. Even more staggering is the distance to Sagittarius A star, the supermassive black hole at the center of our Milky Way galaxy. It's about 25,000 light-years away. Using our fastest spacecraft, the Parker Solar Probe, which can reach speeds of around 700,000 kilometers per hour, it would still take tens of thousands of years to reach just this single black hole. And that's just one black hole among billions in our galaxy alone. So, when we think about reaching a black hole, the first barrier we encounter is simple: the unfathomable scale of space. At present, the fastest spacecraft we have, like New Horizons, are still incredibly slow by cosmic standards. New Horizons, which was launched in 2006 and took 9.5 years to reach Pluto, travels at a speed of about 58,500 kilometers per hour. For a trip to the nearest black hole, it would still take tens of thousands of years, even if it could maintain this speed continuously without interruption. The energy required to travel even this fast is immense. And when you consider the scale of the journey, you realize that human exploration of black holes is beyond the realm of our current technology, at least for the foreseeable future. The distances involved are not the only barrier. There's also the issue of time. Our lifetimes are measured in decades, and even the most advanced spacecraft would require centuries or millennia to reach the nearest black hole. This creates another fundamental problem: human exploration. While it might be possible to send a machine or probe on a journey to a black hole, it is hard to imagine how we could ever send human explorers there. The sheer duration of the trip would demand generational missions, with each successive crew potentially never seeing the outcome of their mission. This introduces an entire host of issues, from maintaining the psychological well-being of long-term crews to the logistics of sustaining human life for centuries during a journey that might not even reach its destination. What makes the challenge even more insurmountable is the physical limitations imposed by the laws of physics. The velocity of our spacecraft is a critical factor. In order to reach a black hole within a reasonable amount of time, we would need to travel at speeds approaching a significant fraction of the speed of light. Currently, our fastest spacecraft are nowhere near that speed, and there are fundamental reasons why it's nearly impossible for any spacecraft to achieve such speeds. According to Einstein's theory of relativity, the closer an object gets to the speed of light, the more energy is required to accelerate it further. As the spacecraft's velocity approaches the speed of light, the amount of energy required becomes infinite. This presents a major issue because, as advanced as our technology may be, we simply do not have the energy resources to achieve the speeds necessary for interstellar travel. Even if we could harness nuclear or antimatter propulsion, which are the leading candidates for future propulsion technologies, they would still not come close to allowing us to reach these cosmic distances within a human lifetime. The energy required to accelerate a spacecraft to even a fraction of the speed of light is far beyond our current power generation capabilities. For instance, the energy required to launch a spacecraft at just 1% of the speed of light would far exceed the total energy consumption of the entire world for thousands of years. The engineering and infrastructure needed to generate such an amount of energy are unimaginable with our current technology. Even theoretical solutions, such as using laser beams or harnessing the power of a star to push a spacecraft forward, still face enormous technical and energy-related challenges. Then there's the issue of fuel. A spacecraft capable of travelling to a black hole at the speeds required would need an immense amount of fuel just to maintain its journey over such long distances. The further the spacecraft travels, the more fuel it would need to keep up the acceleration. This creates a cyclical problem. We need more fuel to get faster, and the faster we go, the more fuel we need. It's an impossible situation when viewed with our current understanding of space travel. Fueling a spacecraft for a journey to a black hole would require resources on a scale we can't yet fathom. Another aspect that makes reaching a black hole virtually impossible is the issue of space debris and cosmic radiation. As a spacecraft approaches the speed of light, it encounters more and more challenges with collisions, even with tiny particles of space dust. A small speck of dust, travelling at high speed, could be enough to destroy a spacecraft. In the vast emptiness of space, this risk is almost negligible at slow speeds. But as we approach faster than light velocities, every microscopic speck of space dust becomes a potential threat. To protect a spacecraft from such damage would require incredibly robust shielding, which again is beyond what current materials can provide. Additionally, cosmic radiation poses a significant risk to human life on long-term space missions. Cosmic rays, high-energy particles that originate from outside the solar system, could pose a grave threat to both the electronics on the spacecraft and the health of any potential astronauts. These particles can cause severe radiation damage to human tissue, DNA, and spacecraft materials, which could lead to a range of health issues, from increased cancer risk to radiation sickness. While there are some proposed shielding techniques that could protect a spacecraft from these high-energy particles, they are still theoretical and unproven on the scale required for such long missions. In conclusion, when we consider the impossibility of reaching a black hole, we confront not just the massive distances, but also the insurmountable technological barriers. From energy requirements to propulsion systems, fuel constraints, and the dangers of space radiation, the obstacles standing between us and even the closest black hole are vast. For now at least, black holes remain beyond our reach. The dream of travelling to one may remain in the realm of science fiction, and even our most advanced technologies may never be able to make that dream a reality. But in the quest to explore the universe, the very impossibility of reaching a black hole is a reminder of the incredible challenges and mysteries that lie ahead. Chapter 7. Black Holes and Spacetime. Black holes represent one of the most extreme distortions in the fabric of space and time. To understand just how incomprehensible these cosmic objects are, we need to look at how they interact with the very nature of the universe. Black holes aren't just dense objects, they are powerful warps in the space-time continuum that can twist and stretch the very rules of physics we take for granted. At the heart of black holes lies a concept rooted in Einstein's theory of general relativity, the idea that gravity is not just a force between two objects, but a warping of space and time itself. General relativity tells us that mass and energy don't just sit in space, they curve it. The more massive an object, the more it curves the space around it. This curvature is so profound in black holes that it creates an environment where traditional laws of physics no longer function in a conventional way. Space-time, the four-dimensional construct of three-dimensional space and time, is stretched beyond recognition near a black hole. Imagine space as a fabric that stretches in response to the presence of mass. A black hole represents a tear in this fabric, one so deep that even light, the fastest thing in the universe, cannot escape. The event horizon is the boundary of this tear, the point beyond which nothing can return, not even information. At the event horizon, space-time curves so sharply that time itself appears to slow down dramatically for an outside observer. From their perspective, anything falling into the black hole would appear to freeze in place, gradually fading away as it crosses the event horizon. But for someone falling in, their experience of time would feel normal. They wouldn't notice any immediate change as they cross this boundary, but they would begin to approach the point of no return, the singularity, where all paths converge. Time dilation, the slowing of time as one approaches a black hole, is one of the most profound implications of relativity. As an object gets closer to a black hole, its experience of time changes relative to an observer far away. To someone standing far away, time appears to stop for anything crossing the event horizon. To the astronauts on board, however, the fall would be immediate. They would not feel any difference until they reach the singularity, the center of the black hole, where space-time becomes infinitely warped. At the singularity, the effects of space-time curvature become extreme. The laws of physics break down, and matter is crushed to infinite density. The concept of distance and time loses all meaning. The singularity is a place where the known laws of the universe cannot explain what happens. It's the ultimate mystery, a place where gravity becomes so intense that it overwhelms every other force in nature. Current theories of physics, including general relativity, cannot describe what happens inside a black hole's singularity. This is one of the major puzzles in modern physics. What happens to space-time under such extreme conditions? Gravitational waves, ripples in the fabric of space-time caused by massive objects like black holes, offer a glimpse into the extreme distortions of space-time that occur in the vicinity of black holes. These waves were first predicted by Einstein in 1916, but it wasn't until 2015 that scientists finally detected them using the Laser Interferometer Gravitational Wave Observatory, LIGO. When two black holes merge, they send out waves that travel across the universe, causing tiny disturbances in space-time that can be measured by extremely sensitive instruments. The detection of these waves has opened a new window into the study of black holes and space-time, allowing scientists to observe cosmic events that were previously beyond our reach. The detection of gravitational waves, however, brings forth another aspect of black holes, their role in shaping the universe on the larger scales. These waves carry information about the black hole merger that produces them, such as the masses of the black holes involved, their spin rates, and the structure of space-time around them. By studying these waves, scientists can better understand the properties of black holes, their formation, and their interactions with the surrounding space-time. It's as if the universe is whispering its secrets to us, and gravitational waves are the key to decoding them. Despite the incredible strides we've made in understanding black holes, the effects of space-time near them remain largely theoretical. The nature of space-time itself is still a mystery, especially when considering the extreme conditions that arise near a black hole. The very fabric of space is warped in ways that challenge everything we know about the universe. If space-time can be bent and warped this severely by a black hole, what other secrets does the universe hold? What other phenomena lie beyond our understanding, waiting to be discovered? Understanding black holes and the space-time curvature they create is not just an academic exercise, it has profound implications for our understanding of the universe and the laws that govern it. The fact that black holes challenge the very nature of space-time and time itself suggests that our current models of the universe may be incomplete. These cosmic behemoths serve as laboratories for testing our theories about space, time, and gravity, pushing the limits of what we know about the cosmos. In conclusion, black holes represent the ultimate distortion of space-time, where gravity warps the very fabric of reality itself. The event horizon, the singularity, and the nature of time near a black hole are all part of a cosmic puzzle that still challenges our understanding of the universe. As we continue to study black holes and their effects on space-time, we inch closer to unraveling the mysteries of the cosmos, one mind-bending discovery at a time. Chapter 8: Theoretical Travel to a Black Hole. The concept of travelling to a black hole has long captured the imagination of scientists and science fiction enthusiasts alike. The immense power of these cosmic giants, the sheer wonder of their existence, and the possibility of unravelling the mysteries they hold make black holes a compelling destination. But despite the fascination, the technical realities of reaching a black hole are far more complex than simply packing a spacecraft and heading off toward the great unknown. As of now, reaching a black hole is well beyond our technological capabilities. However, several theoretical methods have been proposed, exploring how humanity might one day approach these enigmatic objects. First and foremost, the distance to black holes remains the greatest barrier. The nearest known black hole is several thousand light-years away, making it inaccessible with current technology. Even our fastest spacecraft, such as the Voyager 1, which has been travelling through space since 1977, has barely left our solar system. At the speed of Voyager 1, it would take over 70,000 years just to reach the nearest star, let alone a black hole. While the thought of exploring a black hole is tantalizing, we first must confront the staggering distances involved in such a journey. Given the limitations of current propulsion technology, there are several theoretical propulsion methods that might allow us to one day reach a black hole. Among these, one of the most intriguing is laser propulsion. Laser propulsion involves using powerful lasers to propel spacecraft at incredible speeds. These lasers would shine intense beams of light onto sails attached to a spacecraft, pushing the craft forward without the need for traditional rocket fuel. One of the key advantages of this technology is that light travels at a constant speed, making it a potential means of propelling spacecraft to high velocities over long distances. The idea of laser propulsion has been gaining traction in recent years, particularly with projects such as Breakthrough Starshot. Breakthrough Starshot is an initiative designed to send tiny, light-powered spacecraft to the nearest star system, Alpha Centauri, in just 20 years. Using laser sails attached to gram-sized probes, the spacecraft would be propelled to 20% the speed of light. The concept is theoretically sound and has excited scientists because it proposes a way to achieve speeds that were previously thought impossible for spacecraft. However, while this technology could potentially allow us to reach black holes at a fraction of the speed of light, there are significant challenges to overcome. For one, the amount of energy required to propel a spacecraft at 20%, the speed of light, is enormous, and creating a sufficiently powerful laser system to achieve that feat is a formidable task. Additionally, laser propulsion technology faces issues related to precise targeting and maintaining a steady trajectory over vast distances. Another proposed method for reaching a black hole is the idea of using a slingshot maneuver. This technique, used by spacecraft such as the Voyager probes and the New Horizons mission, involves using the gravity of a planet or star to slingshot a spacecraft to higher velocities. This method takes advantage of gravitational assists to increase the speed of a spacecraft without expending additional fuel. While slingshot maneuvers are useful for interplanetary travel, using them to reach a black hole would require a much larger system of gravity assists, stretching across vast distances in the galaxy. Given that the closest black hole is not located near any major planetary systems, the practicality of this approach is limited. Furthermore, such maneuvers would still fall far short of the speed necessary to travel to a black hole within a human lifetime. One of the most groundbreaking theoretical methods for black hole exploration involves a concept called the Alcubierre drive, or warp drive. This idea, first proposed by physicist Miguel Alcubierre in 1994, suggests that faster-than-light travel could be achieved by warping space-time itself. Instead of moving the spacecraft through space at speeds faster than light, the Alcubierre drive would contract space-time in front of the spacecraft and expand it behind, creating a warp bubble that carries the spacecraft along within it. In this scenario, the spacecraft itself would not be traveling faster than the speed of light. Rather, the space around it would be moving. This idea is based on the principles of general relativity and opens up the tantalizing possibility of reaching a black hole in a fraction of the time it would take, using traditional propulsion methods. The challenge with the Alcubierre drive, however, is that it requires a form of exotic matter, substances with negative energy or mass, something that has yet to be discovered or created. Additionally, the energy requirements to manipulate space-time in this way are mind-bogglingly large. Estimates suggest that to create a warp bubble capable of transporting a spacecraft, the energy required could be equivalent to the mass energy of an entire planet. Until we find a way to harness exotic matter or significantly reduce the energy required, the Alcubierre drive remains purely theoretical. Beyond propulsion methods, the very nature of approaching a black hole raises additional concerns. Even if a spacecraft could travel at a significant fraction of the speed of light, the black hole's event horizon, the boundary beyond which nothing, not even light, can escape, presents an impenetrable barrier. No spacecraft, no matter how fast or technologically advanced, can cross this boundary and return. The event horizon represents the ultimate point of no return, a place where the laws of physics, as we understand them, break down. While we can study black holes from a safe distance and gather data using telescopes and space probes, entering a black hole itself would be a one-way trip, with no possibility of communication or retrieval. In conclusion, while there are several theoretical methods for reaching a black hole, all of them come with significant challenges. The distances involved are vast, the propulsion methods are theoretical, and the dangers posed by the black hole itself are insurmountable. While it may be possible to send probes to study black holes from a safe distance, the idea of humans traveling to and surviving a black hole remains firmly in the realm of science fiction. As technology continues to advance, humanity may one day develop new methods for exploring these cosmic giants. But for now, reaching a black hole remains an unattainable dream. Chapter 9. The Effect of Mass on Black Holes. Black holes are one of the most fascinating objects in the universe, and understanding how their mass affects them is key to comprehending their power and influence. Black holes vary widely in terms of their size, mass, and behavior. The mass of a black hole determines many of its key properties, including its size and the strength of its gravitational field. The mass of a black hole is directly related to its event horizon, the boundary beyond which nothing, not even light, can escape. The relationship between the black hole's mass and the size of the event horizon is linear. The greater the mass, the larger the event horizon. A stellar mass black hole, which can have a mass up to 10 times that of the Sun, will have an event horizon of just a few kilometers. However, a supermassive black hole, which can be millions to billions of times more massive than the Sun, will have an event horizon stretching to the size of a solar system. The more mass a black hole has, the more its gravitational pull warps space-time, making its influence felt across vast distances. For stellar mass black holes, which form from collapsing stars, their gravitational pull is strong enough to trap anything that gets too close. These black holes may be relatively small in size, but they can still cause dramatic changes in their surroundings. The collapse of massive stars to form black holes can lead to violent events like supernovae, which scatter heavy elements into space, playing a role in the formation of new stars and planets. Supermassive black holes, found at the centers of galaxies, are even more massive and have a profound effect on their surroundings. These black holes can range from millions to billions of times the mass of the Sun. Due to their immense mass, they generate enormous gravitational forces that warp the space-time around them. These forces not only affect stars and gas clouds in the immediate vicinity, but can also influence the motion of entire galaxies. For instance, galaxies like our own Milky Way have supermassive black holes at their centers, and their mass influences the rotation and behavior of stars in the galaxy. The impact of a black hole's mass doesn't end with its size. The greater the mass, the stronger its tidal forces. Tidal forces occur when different parts of an object are pulled at different rates by the black hole's gravitational field. As an object approaches a black hole, the gravitational pull on the side nearest the black hole becomes much stronger than on the far side. This difference in gravitational pull can stretch and rip apart objects in a process called spaghettification. For stellar mass black holes, the tidal forces can destroy objects far before they even reach the event horizon. However, for supermassive black holes, the tidal forces near the event horizon are weaker, allowing objects to approach much closer without being torn apart, though they still experience extreme gravitational effects. A fascinating aspect of black holes is how mass affects their evolution. As black holes consume more mass from their surroundings, they grow larger and more powerful. This means that black holes can continuously increase in mass as they absorb gas, dust, and even stars that wander too close. The mass of a black hole can also influence its behavior in the larger universe. For example, supermassive black holes can power active galactic nuclei, AGN, regions at the centers of galaxies that emit intense radiation as matter falls into the black hole. This energy can have a profound effect on the galaxy, regulating star formation and shaping the structure of the galaxy. The relationship between mass and gravity is not just important for understanding the behavior of individual black holes. It also has implications for the overall structure of the universe. Supermassive black holes play a key role in the dynamics of galaxies and the formation of large-scale structures in the cosmos. The gravity of supermassive black holes can help regulate the distribution of stars and galaxies within a cluster, guiding their formation and evolution over billions of years. In conclusion, the mass of a black hole is central to its properties, size, and influence on the universe. The larger the mass, the stronger its gravitational pull, the larger its event horizon, and the greater its effect on its surroundings. Stellar mass black holes and supermassive black holes behave differently due to the disparity in mass. But both types of black holes have a significant impact on the space around them. The mass of a black hole also determines its growth, its interaction with nearby objects, and its ability to affect the structure of galaxies and the universe itself. Chapter 10. The Cosmic Scale. How far are we from reaching one? The vastness of space is difficult to comprehend. Black holes, one of the most mysterious objects in the cosmos, are located at unimaginable distances. These cosmic giants captivate our imaginations, but how far are they really from us? And what does this mean for humanity's ability to ever reach one? The closest known black hole to Earth is around 1,000 light-years away. While this might seem manageable, the reality is different. A light-year, the distance light travels in a year, is roughly 9.46 trillion kilometers. Even the nearest black holes are thousands of trillions of kilometers away, making them unreachable with current spacecraft. The distance alone makes this journey seem impossible. The Parker Solar Probe, launched in 2018, is the fastest spacecraft ever built, traveling at speeds up to 700,000 kilometers per hour, nearly 7 times faster than a commercial jet. Even at this speed, it would still take tens of thousands of years to reach the nearest black hole. This highlights the vast challenges we face in reaching these distant objects. The difficulty isn't just about speed, it's about the energy required to propel a spacecraft across such immense distances. To reach a black hole, we would need propulsion systems capable of achieving speeds and energy outputs far beyond current technologies. Even theoretical propulsion methods, such as nuclear fusion or antimatter, require energy levels that are beyond what our civilization can provide at the moment. The distances are simply too vast, and the resources too immense. Then there's the issue of time. Humanity's longest space missions, like the Voyager probes, have taken decades to travel only a fraction of the distance needed to reach a black hole. These missions are remarkable accomplishments, but serve as a reminder of the scale of the cosmos. If we were to send a mission today, it could take hundreds or thousands of years to reach a black hole, requiring us to consider intergenerational missions, where no one alive today would live to see the destination. The problem is compounded by time dilation, a phenomenon predicted by Einstein's theory of relativity. As an object moves closer to the speed of light, time for that object slows down relative to the observer. If we were able to travel close to light speed, the passage of time would be drastically different for those on the spacecraft compared to those back on Earth. For the traveler, the journey would feel much shorter than the hundreds or thousands of years it would take for people on Earth to witness the arrival. Why reach a black hole in the first place? Black holes are inhospitable, with extreme gravitational forces and no known way to survive crossing their event horizon. Yet the pursuit of understanding them is driven by scientific curiosity. Black holes are cosmic laboratories where the laws of physics break down. They provide a unique opportunity to explore gravity, spacetime, and the origins of the universe. Despite the challenges, can humanity ever manage to reach a black hole? The short answer is no, at least not with current technology. The distances involved are too great, and we lack the propulsion systems to cover such distances in a reasonable time frame. But this doesn't mean the dream should be abandoned. History shows that seemingly impossible goals often become achievable with progress and innovation. In the future, new propulsion systems, a deeper understanding of physics, and breakthroughs in space-time manipulation may make such journeys possible. As we continue to study black holes from a distance, our efforts may one day lead to the ability to travel vast cosmic distances. But for now, we remain grounded on Earth, pondering the mysteries of black holes, knowing that while the journey may be beyond our reach, the quest for knowledge is a journey that never ends. Chapter 11. The Singularity. What lies beyond? The singularity, the heart of every black hole, remains one of the most perplexing concepts in modern physics. It is a point where the laws of physics, as we know them, break down, and both space and time cease to function in any meaningful way. But what exactly lies within this enigmatic core? To understand the singularity, we first need to explore the nature of a black hole itself. A black hole is formed when a massive star collapses under its own gravity, compressing its mass into an incredibly dense point. This collapse continues until the star reaches a state of infinite density, creating the singularity. At this point, all the matter that once made up the star is compressed into an infinitely small volume, a place where gravity is so strong that it distorts space-time beyond recognition. As you approach the event horizon, the boundary beyond which nothing can escape from the black hole, you're drawn closer and closer to this singularity. But once you cross that point, escape becomes impossible. Not even light can break free from the gravitational pull, and time itself slows down, eventually halting at the singularity. Here, the very concept of time as we experience it vanishes. But what happens inside the event horizon beyond the reach of our current understanding of physics? According to Einstein's theory of general relativity, once you cross the event horizon, you're on an irreversible path toward the singularity. Everything within the black hole is pulled toward this singularity, where space-time becomes infinitely curved. But this is where things get tricky. While general relativity predicts this catastrophic collapse, quantum mechanics, the theory that governs the microscopic world, suggests a very different scenario. The primary issue here is the breakdown of our understanding of both quantum mechanics and general relativity at such extreme conditions. The two theories are incompatible at this scale. General relativity sees the singularity as a point of infinite curvature, while quantum mechanics is all about uncertainty and probability, which doesn't jive with the certainty of infinite density. This conflict is at the heart of one of the biggest unsolved problems in physics. One of the most fascinating ideas to emerge from this conflict is the concept of quantum gravity. This hypothetical theory would attempt to merge the principles of quantum mechanics with the effects of general relativity, explaining the behavior of matter and energy at the extremes of space and time. Some physicists believe that when you apply quantum mechanics to the singularity, you might avoid the infinite density and instead find that the collapse reaches a limit. In essence, the collapse might bounce back in a quantum mechanical manner, avoiding the infinite compression and allowing for a new universe to emerge from the black hole's core. This theory leads to another mind-bending possibility, the idea that our entire universe could have originated from the collapse of a previous one, inside a black hole. This quantum bounce could potentially be the beginning of an entirely new cosmos, with a fresh set of physical laws, time, and space. If this is true, every black hole could serve as a portal to a new universe, an idea that pushes the boundaries of both cosmology and philosophy. Our own universe, then, could be one of countless others, each born from the collapse of a previous cosmic structure. While these ideas are exciting, they remain speculative. The truth is, we may never fully understand what lies inside the singularity. The current laws of physics are not enough to describe the conditions at such extremes. It's possible that new laws, not yet discovered, govern the behavior of matter and energy inside a black hole. As of now, all we have is mathematical models, which, though elegant, are still far from definitive. But perhaps the most intriguing aspect of the singularity is not what happens inside it, but rather what it represents. The singularity is a point where the known laws of physics break down entirely. It is the ultimate symbol of the unknown, of the limits of our understanding. It reminds us that the universe is still full of mysteries that even our most advanced scientific theories cannot explain. It stands as a reminder that there is always more to discover, more to understand, and more to explore. In the end, the singularity is not just a physical phenomenon, it is a symbol of the frontier of human knowledge. It is a place where science, philosophy, and imagination meet, where we are forced to confront the limits of our comprehension and to imagine what might lie beyond them. The singularity may remain forever elusive, but its mystery will continue to inspire scientists and dreamers alike to look deeper into the cosmos and ask the most fundamental questions about the nature of existence itself. Chapter 12: The Spacecraft and Propulsion Problem. One of the greatest challenges humanity faces in attempting to reach a black hole lies not just in understanding them, but in finding ways to actually get there. Even with the most advanced technology at our disposal, the question of how to travel to the nearest black hole remains a distant dream, hindered by seemingly insurmountable obstacles in space propulsion and energy requirements. At the heart of this issue is the fact that the fastest spacecraft we have today, like Voyager 1 or New Horizons, are slow when put in the context of cosmic distances. Even the most cutting-edge engines, such as those used in the Parker Solar Probe, which can achieve incredible speeds by using gravitational assist from the Sun, still fall drastically short of the velocity needed to approach a black hole in any reasonable time frame. These probes, though remarkable in their accomplishments, are still moving too slowly compared to the vast distances that separate us from distant celestial objects, including black holes. The speeds that current spacecraft can achieve are measured in thousands of kilometers per hour. However, for comparison, the closest black hole to Earth, located in the system of V616 Monocerotis, is about 3,000 light-years away. A light-year, the distance light travels in 1 year, is roughly 9.46 trillion kilometers. At the speed of New Horizons, which travels at about 58,500 kilometers per hour, it would take more than 50,000 years to reach just this one black hole. The mind-boggling scale of time involved reveals just how far we are from any meaningful exploration of these cosmic giants. To put the scale in perspective, consider the concept of the escape velocity needed to break free from a black hole's gravitational pull. The escape velocity is the speed at which an object needs to travel to escape the gravitational influence of a planet, star, or black hole. For any object to reach a black hole, it would need to overcome the gravitational forces at play. But the problem is that, in the case of a black hole, escape velocity exceeds the speed of light. The paradox is clear. If we can't break the laws of physics and exceed the speed of light, how can we even approach something that exists under such extreme conditions? Future propulsion technologies could help address these issues, but the energy demands to power these systems are immense. Concepts like nuclear fusion, antimatter propulsion, and ion drives have all been proposed, but each comes with its own set of limitations. Nuclear fusion, for example, could potentially provide an immense amount of energy, but the technology to harness this energy in a controlled manner is still far from ready. Antimatter, though promising, remains highly theoretical and incredibly difficult to produce and store in quantities large enough to make a dent in the propulsion needs of interstellar travel. Ion propulsion, which is already being used in some of our spacecraft, could be a viable alternative for longer missions, but it still takes an unreasonably long time to accelerate spacecraft to the required speeds. Ion thrusters work by expelling charged particles at high speeds, creating thrust, but their efficiency is limited by how long it takes to reach even a fraction of the speed required to reach distant stars, let alone black holes. To make the leap from theoretical concepts to practical applications, much more research and development is needed. Concepts like laser sails, where lasers could be used to push lightweight spacecraft to a significant fraction of the speed of light, are incredibly ambitious, but face significant hurdles. Pushing even tiny spacecraft to such speeds would require an enormous amount of energy. And even if successful, this technology wouldn't eliminate the challenges of reaching a black hole. The journey would still take many decades, if not centuries, and that's assuming the technology works as intended. and once these tiny spacecraft near their destinations, they would face further challenges such as radiation damage and material degradation due to the hostile environment of space. But one of the biggest hurdles in any potential mission to a black hole is energy. The sheer amount of fuel required to accelerate a spacecraft to even a fraction of the speed needed for interstellar travel is beyond our current capabilities. The energy needed for such a mission could easily surpass the total energy output of the Earth. If a spacecraft were to use traditional chemical propulsion, it would be unable to carry enough fuel to sustain the journey. Even with advanced nuclear or ion engines, the energy demands would be astronomical. To understand just how far we are from practical interstellar travel, we need to consider not just the propulsion systems themselves, but the infrastructure required to support such missions. Building spacecraft capable of long-duration missions to distant black holes would require advances in space-based manufacturing, energy generation, and life support systems. And these advances would need to happen on a scale far beyond anything we've achieved in space exploration so far. For example, the possibility of generation ships, spacecraft that could carry entire generations of humans to their destination, introduces a whole new set of challenges. Not only would we need a reliable propulsion system, but we would also need to account for the survival and sustainability of life for the entire duration of the journey, potentially spanning hundreds or even thousands of years. Food, water, air, and waste management systems would need to be self-sustaining, and advanced systems would need to be in place to maintain human health over such long periods of time. While the challenges of propulsion and energy may seem insurmountable, they are not entirely without hope. Scientists continue to push the boundaries of what we understand about space travel and propulsion. New technologies are being developed and new theoretical frameworks are being explored, but for now, the vast distances to black holes, combined with the limitations of our technology, make it clear that reaching one is a distant dream. In conclusion, while we may one day develop the technologies necessary to travel to black holes, the reality is that we are far from that moment. The challenges we face are not just technological, but also physical, requiring breakthroughs in propulsion, energy production, and the very laws of physics. Until then, the black hole remains one of the greatest mysteries of the universe, a destination we can only dream of reaching. But as science continues to evolve, so too does our understanding of what's possible in the vast, uncharted expanse of space. Chapter 13. Time versus human lifespan. The notion of time as a linear and predictable force has long been ingrained in human consciousness. From the moment we wake up to the time we fall asleep, we measure our lives in years, months, days, and minutes. Time moves forward for us all, and with each tick of the clock, the days and years stack up, each one a stepping stone in our journey through life. But when we look at space travel, and more specifically the idea of reaching a black hole, time suddenly becomes a far more complicated and ominous concept. To imagine a mission to a black hole, one must first confront the reality that human lifespans are simply too short to undertake such a monumental journey. Even if the spacecraft were to travel at the speed of the fastest current technology, such as the Parker Solar Probe or New Horizons, the trip would still span several lifetimes. The journey to the nearest black hole, located in the V616 Monotherotis system, is estimated to be about 3,000 light-years away, a distance that our fastest spacecraft could only begin to approach in several tens of thousands of years. The sheer scale of the journey becomes overwhelmingly clear when we consider the speed at which spacecraft like Voyager 1 are travelling. Launched in 1977, Voyager 1 is the farthest human-made object from Earth, travelling at a speed of about 38,000 miles per hour, 61,000 kilometres per hour. However, even at this speed, it would take around 70,000 years to reach just one of the nearest stars, Alpha Centauri, let alone a black hole. The problem isn't just the distance, but the simple fact that the human lifespan isn't built to sustain such vast stretches of time. This brings up the question, how do we even begin to reconcile the enormous timescales required to reach a black hole with our finite existence? For many, this presents an insurmountable challenge, not just for current spacefaring efforts, but for any future attempt to send humans or even robotic probes to the event horizon of a black hole. The challenge lies not in the technology, though that is a hurdle in itself, but in the nature of the voyage. How do we maintain a mission across multiple generations? While robots may be able to go the distance and transmit data back to Earth for many years, humans would face a far greater dilemma. The idea of a generational mission, where different generations of astronauts are born, live, and die aboard the spacecraft, seems a more feasible approach. However, this concept raises an even more difficult question about how the human spirit would endure the psychological toll of such a mission. Could an entire civilization endure being cooped up in a spacecraft for generations, knowing they may never return to Earth? The notion of time becomes far more personal in this context. It isn't just about the future of the universe, but about the well-being and mental resilience of the travelers who would never get to witness the completion of the journey. This long-term journey concept has its roots in the idea of a generation ship, which is essentially a spacecraft designed to carry multiple generations of humans on a long voyage, with the hope that descendants of the original crew will eventually reach the destination. But this concept is fraught with logistical and psychological challenges. How do you preserve the culture, the knowledge, and the spirit of a society when the journey lasts far longer than any one lifetime? At the same time, it's important to acknowledge that space exploration has historically been a venture of the human spirit, driven by curiosity, ambition, and the desire to explore the unknown. Yet when we're dealing with the vastness of space, that sense of human curiosity clashes with the finite nature of human existence. A journey to a black hole would force us to confront the question, how do we reconcile the human need for immediacy with the slow, almost glacial march of space? The time factor isn't just a theoretical or logistical issue, it's an emotional one. Would astronauts on a multi-generational mission even consider the mission worth it, knowing that the trip would span so many lifetimes that it would become a kind of collective memory, one where their direct contributions might not be seen by any living being? This burden of time might alter the very fabric of motivation for those embarking on the journey, as the psychological toll of working on something that takes so long to achieve could wear down even the most resilient minds. Moreover, time affects not just the astronauts, but everyone back on Earth. It's impossible to overstate the psychological toll on those left behind. The idea of an endeavour spanning generations brings to light a new kind of loneliness, a loneliness that stretches far beyond space and into the hearts of those who will never see the mission's fruition. As the decades go by, family members and generations that would have been born and died in the interim would have little more than distant stories to keep them connected to the mission. It would become an idea, a myth, something their ancestors did long ago, and the psychological impact of that could have profound effects on the human psyche. It's easy to imagine space exploration as a constant forward march of discovery, where progress is constant and the next milestone is always within reach. But in the case of a journey to a black hole, time itself becomes the obstacle. It becomes the measuring stick for human progress, and in doing so, forces us to confront our own limitations as a species. In conclusion, the idea of reaching a black hole isn't just about the physical obstacles of propulsion and energy. It's about the human costs, the long-term sacrifices, and the unimaginable psychological toll of a voyage that might take multiple generations to complete. Time is the ultimate barrier in this endeavour, forcing humanity to confront the impossible question: can we, as a species, endure for so long? And if so, is it worth it? The future of humanity's exploration into black holes might well depend on how we grapple with these questions. understanding that time, in all its vastness, might be the one challenge we cannot overcome. Chapter 14. Quantum Mechanics and Black Holes. Quantum mechanics, the study of fundamental particles, is full of strange and counterintuitive phenomena that challenge our classical understanding of reality. Black holes, cosmic entities that warp space and time, present one of the greatest mysteries in physics. Understanding how quantum mechanics and black holes interact may offer solutions to some of the deepest puzzles in science. At its core, quantum mechanics suggests that particles like electrons and photons don't behave as expected in our everyday world. Instead, they exist in superposition, where they can be in multiple places at once until observed. This principle leads to behaviors like quantum entanglement, where particles instantaneously influence each other, even across vast distances. When these quantum effects intersect with black holes, they bring new challenges to understanding the nature of space, time, and gravity. Black holes are defined by their event horizon, a boundary beyond which nothing, not even light, can escape. Standard theories suggest that anything crossing this event horizon gets crushed into a singularity, a point where gravity overwhelms all other forces and space-time breaks down. But quantum mechanics suggests a different story. In the 1970s, Stephen Hawking proposed a theory based on quantum mechanics that contradicted the classical view of black holes. His theory of Hawking radiation posits that black holes emit radiation due to quantum fluctuations near the event horizon. Normally, pairs of virtual particles spontaneously appear and annihilate each other. However, near a black hole, one particle can be pulled into the black hole while the other escapes. This process means black holes slowly lose mass and energy over time and could eventually evaporate. Hawking radiation challenged the idea that nothing could escape a black hole, suggesting that black holes are not entirely black and can shrink over time. This theory introduced the black hole information paradox, which arises from the fact that quantum mechanics insists that information cannot be destroyed. But according to general relativity, once matter crosses the event horizon of a black hole, it is lost to the universe. If black holes emit radiation, where does the information go? Does it escape with the radiation, or is it lost forever? This paradox has puzzled physicists for decades and sparked numerous debates on the true nature of black holes. One key element of this paradox is the concept of quantum gravity, the attempt to combine quantum mechanics and general relativity into a single theory. Quantum gravity has the potential to explain how gravity behaves on the smaller scales, something that general relativity cannot do. One promising theory, loop quantum gravity, suggests that space-time is quantized, meaning it's composed of discrete units, rather than being continuous. If this theory is correct, it could help explain what happens at the singularity, where classical physics breaks down. Another theory, string theory, proposes that the fundamental components of matter are not point-like particles, but tiny, vibrating strings. This theory also attempts to unify the forces of nature, including gravity, and could provide insights into the quantum nature of black holes. However, both loop quantum gravity and string theory are still works in progress, and their ability to explain black holes remains uncertain. The development of Hawking radiation led to further advances in understanding black holes at the quantum level, but the paradox of information loss still persists. Some researchers propose that the information is not lost, but instead is encoded in the radiation that escapes from the black hole. Others believe that the event horizon might not be a solid boundary after all, and that quantum effects could allow information to leak out over time. However, these ideas remain speculative, and there's no definitive answer yet. Despite these ongoing debates, it's clear that quantum mechanics plays a significant role in shaping our understanding of black holes. The merging of quantum mechanics and general relativity is one of the greatest challenges in physics today. Quantum mechanics governs the smallest scales of the universe, while general relativity explains the behavior of large objects, like black holes. If we can combine these two theories, it could revolutionize our understanding of space, time, and gravity. In conclusion, the connection between quantum mechanics and black holes remains one of the most mysterious and exciting areas of modern physics. Hawking radiation, the information paradox, and the search for a theory of quantum gravity all point to the fact that the study of black holes at the quantum level holds the key to unlocking some of the most profound mysteries of the universe. Though many questions remain unanswered, the journey to understand black holes is far from over. Every step forward in this field brings us closer to a deeper understanding of the fundamental forces that govern the cosmos. Chapter 15. Proxima B, Earth-like but hostile. Proxima B, the first exoplanet discovered orbiting the closest star to our Sun, Proxima Centauri, lies just over 4 light-years away from Earth. It has tantalized astronomers since its discovery, hailed as one of the most Earth-like exoplanets we know. With a similar size and positioned within the star's habitable zone, Proxima B has sparked the imagination of those hoping to find another Earth, a potential new home for humanity. However, the very characteristics that make it a potential haven also raise fundamental questions about its habitability. At first glance, Proxima B seems to have all the right conditions to sustain life. Its proximity to its host star places it in the so-called Goldilocks zone, where temperatures might allow liquid water to exist, one of the key ingredients for life as we know it. In this sense, it shares many of the conditions that allowed Earth to nurture life, but a closer inspection reveals significant obstacles that complicate the idea of life flourishing there. The first major hurdle comes from Proxima Centauri itself, a red dwarf star known for its instability. Unlike our Sun, which is relatively stable, red dwarfs are prone to powerful and unpredictable flares. These violent outbursts of radiation, often hundreds or even thousands of times stronger than what the Sun emits, could strip away any atmosphere Proxima B may have, leaving the planet exposed to deadly levels of ultraviolet radiation. This makes the prospect of habitability on Proxima B far less certain than we would hope. Another challenge arises from the fact that Proxima B is likely tidally locked to its star. This means one side of the planet perpetually faces the star, while the other remains in perpetual darkness. The side facing the star would experience extreme heat, while the far side could be frozen in an eternal night. The resulting temperature extremes could make it impossible for stable, life-sustaining environments to form, especially considering the uncertainty of whether Proxima B has an atmosphere thick enough to distribute heat evenly across the planet. If its atmosphere is thin or non-existent, the planet would be subject to extreme temperature gradients, possibly making it inhospitable for life as we know it. The threat of Proxima B's habitability goes beyond its hostile environment. The planet's star, Proxima Centauri, is known to be highly active in its younger years. As a result, any planet orbiting within its habitable zone would have faced bombardments of intense radiation during its early formation stages. This radiation could have had catastrophic consequences, including the sterilization of the planet's surface and the destruction of any potential early atmospheres. Even if Proxima B had the right chemical ingredients to support life, these early violent events could have wiped the slate clean, leaving the planet without the necessary conditions for biological evolution to take place. Yet despite these challenges, Proxima B remains a fascinating subject for study. With its Earth-like size, location in the habitable zone, and proximity to Earth, it offers an unparalleled opportunity to test our understanding of planetary conditions and the prospects for life beyond our solar system. However, it also forces us to reconsider what it means to be Earth-like. Life on Earth thrives in a very specific set of conditions, and Proxima B, while similar in some ways, is far more extreme than our planet in others. The discovery of Proxima B emphasizes the broader lessons about the search for life in the universe. While we can imagine Earth-like planets in distant solar systems, we must also confront the realization that such planets may not be as habitable as we expect. The idea of an Earth 2.0, a planet that mirrors the conditions of our own and harbors life, is far from guaranteed. Just because a planet lies within the habitable zone of a star doesn't necessarily mean it can support life. As our understanding deepens, we see more clearly that many factors, from radiation and atmospheric conditions to tidal locking and stellar activity, can make even the most promising planets uninhabitable. In the coming years, missions like the James Webb Space Telescope, JWST, will allow us to peer deeper into the atmosphere of planets like Proxima B, analysing their chemical makeup and the potential for life-supporting conditions. But until we have more data, the dream of Proxima B as another Earth remains just that. A dream filled with possibility, yet surrounded by many uncertainties. As the search for other Earths continues, Proxima B serves as a reminder of the complex nature of habitability. While it offers hope, it also challenges us to reconsider our assumptions about what makes a planet truly suitable for life. Perhaps as we learn more, we will find that the true nature of exoplanets like Proxima B isn't about finding another Earth, but about understanding the vast diversity of worlds in the universe and the unique conditions that shape each one. Until then, Proxima B remains a distant, enigmatic world, close enough to imagine, yet far enough to remind us how little we truly know about the cosmos. Chapter 16. Exploration without arrival. The idea of exploring distant, unimaginable places like black holes brings with it the desire for more than mere observation. We seek to touch the unknown, to land on planets, to understand the mysteries of deep space by getting closer. However, when it comes to black holes, our very concept of exploration is fundamentally changed. The quest for knowledge, as noble as it is, comes with an almost insurmountable obstacle: the inability to reach the things we yearn to understand most. Black holes represent an exploration without arrival, a journey to the outermost limits of space and time, with no promise of ever reaching the destination. The first limitation, and perhaps the most profound, is the very nature of black holes themselves. They are defined by their event horizon, a boundary beyond which nothing, not even light, can escape. Once any object crosses this boundary, it is doomed to be pulled into the singularity, the point of infinite density, where the laws of physics, as we understand them, break down. The event horizon is a one-way boundary, a one-way street to oblivion. And once we venture past it, there is no turning back, no way of transmitting information back to our own universe. For any probe, spacecraft, or even hypothetical human explorer attempting to approach a black hole, this boundary spells the end of their journey. The black hole's gravity grows stronger as one gets closer, and at the event horizon, time itself begins to slow down dramatically. From the perspective of an outside observer, time seems to freeze as an object nears the event horizon. To someone falling in, it would appear that time continues as normal. But no signal, no matter how fast, could ever reach the outside world once it crosses the event horizon. This means that while we can imagine probes travelling toward a black hole, we know that they can never return with their data. We would never receive first-hand information about what happens beyond the event horizon. This is a grim reality of black hole exploration. The deeper we reach into their mysteries, the more we realize that our exploration becomes one of absolute one-way exploration. The possibility of sending data back to Earth becomes a theoretical concept, an effort that falls short of the ultimate dream of space exploration. On top of this, there's the issue of the vast distances separating us from these black holes. The closest known black hole, named a 0620-00, is about 3,000 light-years away. The journey to even observe one of these black holes at a relatively close range, using the fastest technology available today, would take tens of thousands of years, far longer than the lifespan of any spacecraft we could build. This immense distance only serves to reinforce the overwhelming reality that no human and no probe we currently possess can feasibly travel to a black hole, let alone return with valuable data. Another crucial factor is the technology. While we have made impressive strides in space exploration, the current propulsion systems simply don't allow us to travel at anywhere near the speeds required for long-distance interstellar travel. Even with propulsion breakthroughs such as nuclear fusion or theoretical concepts like antimatter engines, we are still looking at travel times that would span centuries or longer. Sending a probe to a black hole would take us far beyond the reach of our technology, and that's before considering the technological challenges of surviving the trip in the extreme conditions found near a black hole. Consider the immense radiation surrounding a black hole. As matter gets drawn in, it accelerates to nearly the speed of light and generates intense radiation in the form of X-rays and gamma rays. Even a spacecraft designed to withstand these radiation levels would be challenged by the constant bombardment of energy. The closer one gets to the black hole, the more the environment becomes hostile. Even if a probe could withstand the radiation, the question of how to survive the sheer physical forces at play, like tidal stretching and spaghettification, remains unresolved. Once again, humanity's desire to explore cannot overcome the fundamental conditions that make black holes dangerous. Yet despite these overwhelming obstacles, we continue to observe black holes from afar, using the most advanced telescopes and technology at our disposal. The Event Horizon Telescope, which captured the first image of a black hole's event horizon, was a historic achievement. It allows us to view black holes as never before. But even this breakthrough is a form of exploration without a rival. We can only peer into the darkness. We can never fully experience it. This paradox lies at the heart of our cosmic curiosity. Black holes are among the most intriguing objects in the universe, yet the very characteristics that make them fascinating, their power, their danger, their ultimate isolation, also make them unreachable. While we may observe them, we cannot directly engage with them. Our exploration, as thrilling as it is inherently incomplete. We may never have the ability to understand or explore them in the way we desire. However, the limitations of space exploration do not signal the end of the story. Our understanding of black holes and the laws of physics continues to evolve. As we learn more, we continue to get closer to unraveling their mysteries, even if we can never physically enter the event horizon. Just because we cannot reach them doesn't mean we cannot understand them, and that understanding will forever be a part of our cosmic exploration. In the future, missions may push the boundaries of our understanding and develop new technologies that make the impossible seem achievable. But as it stands, the black hole will remain a place of one-way exploration, never a destination, but always an invitation to seek what lies beyond the known universe. We are left to ponder, what does it mean to explore a cosmic mystery that we can never truly reach? In the case of black holes, the answer may lie not in arrival, but in the journey of discovery itself. Chapter 17: Spacetime and the Impossibility of Breaking Free. The nature of black holes is rooted in one of the most fundamental concepts of physics, space-time itself. When we think about space, we often imagine it as a backdrop, a passive expanse that simply holds stars, planets, and galaxies. But black holes force us to confront a different reality. Space-time is not just a backdrop. It is a dynamic, malleable fabric that can be warped and shaped by gravity. Black holes, as the most extreme examples of gravitational forces, warp space-time to such an extent that they trap everything within their event horizons. The event horizon is the defining feature of a black hole. It's a one-way boundary beyond which nothing can escape, not even light. Once something crosses this point, it is doomed to be pulled into the singularity at the black hole's core, where the laws of physics as we know them break down. But what makes this event horizon so impenetrable? The answer lies in how black holes manipulate space-time. As a massive object like a star collapses under its own gravity, it causes space-time to curve intensely. Imagine a heavy ball placed on a stretched rubber sheet. This creates a depression, a distortion in the sheet. Similarly, a black hole's mass distorts the fabric of space-time, creating a gravitational well so deep that everything within a certain radius, including light, is pulled in. This curvature of space-time means that once anything crosses the event horizon, it cannot escape the gravitational pull of the black hole. The most fascinating and ultimately frustrating aspect of black holes is their one-way nature. From the inside of the event horizon, there is no escape. Nothing, no matter how fast it moves, no matter how much energy it has, can escape the overwhelming gravitational pull. Even though light travels at the fastest speed known in the universe, it too is trapped once it crosses the event horizon. To fully grasp this, we need to understand the concept of escape velocity, the speed at which something must travel to break free from an object's gravitational pull. For Earth, the escape velocity is about 11 kilometers per second, meaning that anything moving slower than that will be pulled back to Earth's surface. For a black hole, the escape velocity at the event horizon exceeds the speed of light. Since nothing can travel faster than light, this means that even light, the fastest thing in the universe, cannot escape the black hole's gravitational grasp. This creates a paradox of sorts. Black holes, by their very nature, are bound by the laws of space-time, and yet they defy our understanding of physics by making escape impossible. One of the most significant challenges of exploring black holes lies in this very concept. Our current understanding of space-time tells us that once something enters a black hole, it cannot return. We are limited by this fundamental barrier in physics. No matter how far our technology advances, no spacecraft will ever be able to break free once it crosses the event horizon. This is what makes black holes so elusive and so fascinating. They represent a point of no return, where escape from their grasp is not just improbable, but impossible. Even as we continue to make breakthroughs in our understanding of black holes, such as imaging the shadow of a black hole or detecting gravitational waves caused by their mergers, we remain fundamentally unable to explore these cosmic mysteries in any direct way. All the data we collect, all the observations we make, are from a safe distance, outside the event horizon. Even the most advanced space probes or hypothetical missions to black holes will never allow us to cross that threshold. In a sense, black holes represent the ultimate barrier to human exploration. They are the limits of space-time, a place where everything we know about the universe, from gravity to light, breaks down. Our technology, our physics, and our very understanding of space and time cannot overcome this barrier. We can study black holes from afar, gathering information through indirect methods, like observing their effects on nearby stars or using gravitational wave detectors. But we cannot truly interact with them in any meaningful way. This is not a flaw of our technology or our imagination. It's a consequence of the fundamental nature of black holes themselves. The immutability of the event horizon forces us to confront the limits of human exploration. Despite our incredible advances in technology and space exploration, we remain powerless to penetrate this boundary. Our reach is forever limited. In this sense, black holes serve as a constant reminder of the limitations inherent in our pursuit of knowledge and exploration. As we continue to push the boundaries of what we can understand about the universe, black holes stand as the ultimate reminder that there are some things beyond our grasp. They are not just distant objects in the sky. They represent the boundaries of what is possible within the fabric of space-time itself. They challenge us to think beyond our immediate goals and aspirations. In the face of such immense forces, we are reminded of how small and fragile we are in the grand scale of the universe. But in acknowledging these limitations, we also recognize the importance of continuing the journey. While we may never be able to cross the event horizon, the quest for knowledge does not end. Black holes may hold the answers to some of the most profound questions about the nature of space, time, and gravity. And while we may never reach them, the effort to understand them pushes us forward into the unknown, challenging our understanding of the universe and the very laws of physics themselves. The journey to explore black holes may never be a physical one, but the intellectual journey is far from over. We may never break free from the event horizon, but our understanding of what lies beyond it will continue to evolve, driving us toward new frontiers in space exploration and cosmology. Chapter 18: Theoretical Space Travel and Black Hole Exploration. As we venture into the concept of black hole exploration, we are met with a daunting realization. The scale, the challenges, and the technological gaps are vast. Yet some theoretical possibilities offer hope for the future, even if the hurdles are staggering. Could humanity, with its endless innovation and persistence, one day send a spacecraft into the dark abyss of a black hole? It's a question that hinges not just on the physical limits of our technology, but also on the deep understanding of fundamental physics that we have yet to uncover. Theoretical missions to black holes are often grounded in our current understanding of general relativity, quantum mechanics, and even speculative ideas from science fiction. The first step in any theoretical mission would be the method of propulsion. Presently, we rely on rocket-based propulsion systems, chemical, ion, and electric. These methods, however, are far from adequate for the journey to a black hole. The vast distances, not to mention the extreme forces at play near a black hole, make it clear that current propulsion methods cannot carry us even close to the event horizon. Theoretical propulsion systems like those using antimatter or nuclear fusion have been proposed. In theory, antimatter propulsion could deliver immense thrust, with the energy density of antimatter providing a potential power source capable of reaching near light speeds. Yet antimatter remains elusive, and even if we manage to create it in a controlled manner, we would face the massive challenge of storing and managing it in a safe, usable form for long-duration space travel. Nuclear fusion, while a promising concept for energy production on Earth, also faces immense obstacles in the context of interstellar travel. The technology needed to create and maintain a self-sustained fusion reaction powerful enough to power a spacecraft over light years of travel has not yet been realized. Even if fusion-based propulsion could one day be achieved, the sheer scale of distance to black holes would still present a significant barrier. One of the most intriguing theoretical ideas for exploring black holes comes from the concept of slingshot maneuvers around black holes, also known as gravity assists. This concept builds on what we already know about using the gravitational field of a planet or moon to gain momentum and speed. When applied to a black hole, a spacecraft could theoretically swing around the black hole in a manner that allows it to gain immense speed without using additional fuel. However, the challenges of such a maneuver are clear. To make a successful gravity assist from a black hole, the spacecraft would need to approach at precisely the right angle, speed, and trajectory. A slight miscalculation, even a tiny deviation, would send the spacecraft into a spiral that could be catastrophic. In addition, the spacecraft would need to be able to survive the extreme tidal forces exerted by the black hole's gravity. No material currently available would likely withstand the sheer stress of approaching such an object. Another idea that has gained traction is the concept of a light sail propulsion system, sometimes dubbed Starshot. The Breakthrough Starshot initiative, supported by leading figures like Stephen Hawking and Yuri Milner, proposes using powerful ground-based lasers to propel light sails, ultra-thin, reflective materials, into space. If the technology works as theorized, it could theoretically propel a small, lightweight spacecraft at up to 20% of the speed of light. While this concept holds exciting potential for interstellar missions, sending a spacecraft to a black hole at this speed would still involve massive challenges. The closest black hole is still about 1,000 light-years away. Even if light sails could travel at 20% the speed of light, this journey would take decades, far too long for any current form of communication or crewed mission. And even at that speed, the spacecraft would still be far from surviving the extreme conditions near the event horizon. At the same time, advances in quantum mechanics may open new doors for understanding space-time and allowing more practical exploration techniques. The use of quantum tunneling, wormholes, and entanglement to travel vast distances could theoretically revolutionize space exploration, though these ideas remain speculative. Quantum tunneling, which allows particles to pass through barriers they traditionally should not be able to, could potentially be harnessed to create a shortcut through space-time, bypassing the massive distances between us and a black hole. Wormholes, if they exist, could also serve as bridges connecting different points in space-time, potentially providing an escape route or entrance to black holes. But as of now, these ideas are theoretical, and the challenges of proving or exploiting them are monumental. Perhaps the greatest hurdle of all is the environment around black holes. Even with advanced propulsion systems, a spacecraft would have to navigate through a sea of dangers. Space near a black hole is filled with intense radiation, gravitational waves, and high-energy particles, all of which could destroy any spacecraft that ventures too close. Understanding how to shield a craft from this lethal environment is a critical part of any theoretical exploration mission. Unfortunately, we currently lack the materials or technology to protect against such extreme conditions, and we have no idea how long a spacecraft could survive in such an inhospitable place. While interstellar space travel is a fascinating prospect, it remains firmly in the realm of theoretical exploration for now. The current technological limitations, combined with the extreme forces at play near a black hole, make it nearly impossible for humanity to launch a successful mission into the depths of a black hole. However, the theories and ideas we explore today could pave the way for future breakthroughs in propulsion, shielding, and space-time manipulation. In the distant future, perhaps humanity will uncover the mysteries of black holes and even find a way to explore these cosmic wonders up close. Until then, we can only imagine what it would be like to journey to the very edge of the universe's most enigmatic objects. Chapter 19. Beyond Observation: The Realms of Speculation. When it comes to black holes, the scientific community has made remarkable progress in understanding their gravitational effects, the formation process, and their interactions with nearby matter. Yet, beyond the well-established facts about their observable behavior, there remains a vast ocean of speculation about what really happens within these cosmic enigmas. What could exist beyond the event horizon? And how might black holes contribute to new understandings of the universe and beyond? These are questions that provoke both scientific inquiry and imaginative speculation. One of the most persistent theories about black holes is the possibility that they might serve as gateways to other realms of existence. The concept of black holes as wormholes, tunnels, or shortcuts through space-time has captured both scientific and public imaginations for years. According to Einstein's theory of general relativity, black holes are regions where gravity is so intense that not even light can escape their grasp. Yet this theory also suggests that space-time itself may be warped within the event horizon, potentially connecting distant regions of the universe. If this is true, then what lies within a black hole may be connected to entirely new realms of space-time, potentially even other universes. The wormhole theory posits that a black hole could lead to a bridge through space-time, creating a shortcut to another part of the universe or even a parallel universe. This idea is rooted in the broader understanding of the universe being made of warped space-time. However, despite the intriguing potential of this theory, there is no experimental evidence to support it. In fact, many experts argue that even if black holes could theoretically be wormholes, they would be highly unstable and would collapse before anything could traverse them. Nonetheless, this idea opens a door to a new realm of possibilities where black holes could act as pathways to other dimensions, dimensions that may exist far beyond our current understanding of space and time. Another fascinating theory surrounding black holes is the concept of information loss. According to classical physics, once something crosses the event horizon, it is lost forever. This suggests that all the information about an object, from its position to its properties, is effectively erased from the universe. But this conflicts with quantum mechanics, which holds that information cannot be destroyed. As a result, a paradox arises known as the black hole information paradox. Some physicists speculate that black holes may not actually destroy information, but instead preserve it in some form, possibly encoding it in the event horizon or through quantum processes that we are still trying to understand. Could black holes be the conduits for new forms of life or new cosmic evolutions? If black holes act as the birthplaces of new universes, as some theories suggest, they could serve as seeds for entirely new realities, with galaxies, stars, and potentially even life growing in environments completely separate from our own. This is where the idea of black holes as generators of universes comes into play. The notion that a black hole, after exhausting its gravitational power and collapsing upon itself, could lead to the formation of a new universe is known as the Big Bounce theory. This idea suggests that the collapse of one universe through a black hole could give birth to a new, separate universe on the other side of the event horizon. This speculation offers a tantalizing perspective on the cyclical nature of the universe, where the death of one cosmos leads to the birth of another. While we cannot observe the interior of a black hole, we can observe its effects on the surrounding environment. Through the study of gravitational waves, for instance, we have been able to detect ripples in space-time caused by black hole mergers. These waves carry valuable information about the mass and behavior of the merging black holes, but they offer only indirect evidence of what is happening inside these mysterious objects. Similarly, the Event Horizon Telescope has provided the first ever image of a black hole's event horizon, giving us a glimpse of its outermost boundary. However, beyond that boundary, all we have is speculation. Furthermore, some scientists speculate that black holes may not even be singularities in the traditional sense. Rather than acting as points of infinite density, where space and time cease to function, black holes may contain unknown quantum processes that preserve the structure of space-time and avoid the infinite destruction predicted by classical general relativity. This is where the quest for a unified theory of quantum gravity becomes crucial, a theory that successfully merges the principles of quantum mechanics and general relativity could one day provide the answers to what truly happens inside a black hole. The speculative nature of black holes extends beyond just theoretical physics. Philosophers and cosmologists have long wondered whether black holes could hold the key to understanding the deepest aspects of existence. If black holes serve as portals to other dimensions or realities, do they reveal that our universe is only one of many in an infinite multiverse? Could the laws of physics, as we understand them, only apply within the confines of our own universe, with entirely different rules governing other realms beyond black holes? If so, then the study of black holes could lead to a profound shift in our understanding of the cosmos and our place within it. In conclusion, while much of what happens inside black holes remains speculative, the mysteries they present are too compelling to ignore. The theories and hypotheses continue to evolve, with each new discovery offering a glimpse into a universe far more complex than we ever imagined. As we continue to observe and study black holes, we may not only uncover new insights into these cosmic giants, but also unravel the deepest questions about the nature of the universe itself. Whether black holes are gateways to other universes, time machines, or the source of new cosmic realities, the journey to understand them will continue to challenge our scientific boundaries and spark our imagination for generations to come. Chapter 20: The Science of Time Travel and Black Holes. Black holes have long captured the imagination of both physicists and the general public, not only for their immense gravitational pull, but also for the mind-bending possibilities they present, including the idea of time travel. The concept of traveling through time seems like something straight out of science fiction, yet black holes, specifically the intense warping of space-time around them, might offer the most scientifically plausible route to time travel. The relationship between black holes, time dilation, and the bending of space-time holds the key to understanding whether time travel is theoretically possible. The foundation for understanding time travel begins with Albert Einstein's theory of general relativity, which reshaped how we think about gravity and space-time. Unlike Newton's view of gravity as a force between masses, Einstein's general relativity presents gravity as the curvature of space-time caused by mass. Massive objects like stars, planets, and black holes cause a significant warping of the space-time fabric, bending it in such a way that time itself is affected. This phenomenon is known as time dilation. Near a black hole, the curvature of space-time is so extreme that time itself slows down relative to an outside observer. For someone falling toward a black hole, time would appear to move normally for them. But from the perspective of an observer far away from the black hole, the person approaching the event horizon would seem to slow down. This effect becomes most pronounced as the object gets closer to the event horizon, the point of no return. At the event horizon, time appears to almost freeze from the distant observer's viewpoint, with light and matter unable to escape the black hole's gravitational grasp. Time dilation is a well-established concept. It has been experimentally confirmed on a small scale using atomic clocks flown on aircraft and placed in satellites, where the clocks in motion tick slower compared to those on Earth. However, the effect near a black hole would be much more dramatic. The closer you get to the event horizon, the stronger the effect, leading to extreme time distortions. This extreme warping suggests that a traveller close to a black hole could experience mere moments, while from an external perspective, potentially centuries pass. But how does this connect to time travel? The time dilation around black holes, particularly those that are rotating or spinning, like the supermassive black hole at the centre of our galaxy, Sagittarius A star, may allow for theoretical pathways into the future. As you approach the event horizon, time speeds up dramatically for those watching from a distant location. While this could mean that one can experience time in the usual sense, it may also allow for a slingshot effect. Those near a black hole could experience a rapid passage of time compared to those far away. While this doesn't allow for backwards time travel, it offers the possibility of travelling forward in time. Another concept tied to time travel involves the rotation of black holes. Theoretical physicists have proposed that rotating black holes, or Kerr black holes, could possess a unique feature known as a closed time-like curve. Essentially, these are paths in space-time where the normal flow of time could be looped back on itself. If this idea holds any merit, a spacecraft travelling along these closed time-like curves could, in theory, loop back to an earlier point in its own timeline. This would be a form of time travel that could, hypothetically, allow a traveller to revisit the past or accelerate through the future. However, closed time-like curves are highly speculative and still lie within the realm of theoretical physics. Yet the idea of backward time travel through black holes presents its own paradoxes. If time could be reversed, it would violate causality. the principle that causes precede effects. This would open the door to logical contradictions, like the famous grandfather paradox, in which a time traveller might go back in time and prevent their own birth. Such paradoxes challenge our understanding of reality and time itself. Hawking's idea of the chronology protection conjecture posits that the laws of physics prevent time travel to the past to avoid these paradoxes. According to this conjecture, nature would find a way to stop such time loops from forming, ensuring that causality remains intact. This would suggest that while black holes might offer a path to the future, they cannot allow one to travel backward in time without violating the laws that govern the universe. To complicate matters further, quantum mechanics also plays a role in the discussion of black holes and time travel. According to quantum theory, particles behave in a fundamentally different way than the classical laws of physics suggest. One of the most puzzling phenomena is quantum entanglement, where two particles, no matter how far apart, remain instantaneously connected. This connection challenges our conventional understanding of space and time. Some theorists believe that quantum mechanics might provide an entirely different view of time and space, one that could potentially offer new ways to understand time travel, though we are far from fully understanding how quantum theory and relativity work together. Despite the many theoretical approaches to time travel through black holes, the overwhelming consensus in the scientific community is that practical time travel is still far out of reach. The energy requirements to approach a black hole, let alone survive its intense gravitational forces, are beyond our current capabilities. Moreover, even if we could approach one safely, the extreme radiation near the event horizon would likely destroy any spacecraft. In conclusion, while black holes and their associated phenomena provide fascinating insights into the fabric of space-time, the concept of time travel remains speculative. The extreme effects of time dilation near black holes could theoretically allow one to travel forward in time, but backward time travel is riddled with paradoxes and challenges that may never be overcome. The study of black holes continues to provide valuable lessons in our understanding of the universe, pushing the boundaries of what we know about space, time, and reality itself. Chapter 21. The Universe Beyond the Event Horizon. The event horizon of a black hole is the ultimate boundary, a one-way surface beyond which nothing, not even light, can escape. Once past this point, the force of gravity is so immense that it overpowers everything we know about physics, leading to a complete breakdown of the laws that govern our universe. But what happens on the other side of this boundary? Is there a beyond, or is it the end of everything we understand? Scientists have long speculated about the nature of the universe beyond the event horizon, as this is one of the most elusive regions of space. To begin to understand what might lie beyond, we first need to explore the characteristics of a black hole itself. According to Einstein's theory of general relativity, the event horizon marks the limit at which the escape velocity exceeds the speed of light. The closer you get to a black hole, the more intense the gravitational forces become, distorting space-time to extreme levels. As we approach the event horizon, time itself begins to slow down, and space begins to warp. To an outside observer, it would appear as though anything falling into the black hole is frozen in time, seemingly suspended forever. But to an object or person falling into the black hole, time would seem to proceed normally, even as they approach the singularity, the point of infinite density at the center of the black hole. The idea of what lies beyond this point remains one of the greatest mysteries of modern cosmology. For a long time, it was believed that once an object crossed the event horizon, it would be crushed into nothingness at the singularity. The matter would reach infinite density, and all information about its composition would be lost. This was the no-escape scenario. However, recent advancements in theoretical physics, particularly in the realm of quantum mechanics, suggest that the situation might be far more complex and intriguing. In quantum mechanics, the concept of information is fundamental. The no information loss principle suggests that all information, even if it falls into a black hole, is preserved in some form. This theory contradicts the classical view that information is lost at the singularity. One possible explanation for this paradox lies in the concept of Hawking radiation, proposed by physicist Stephen Hawking in the 1970s. According to Hawking's theory, black holes are not completely black. They emit radiation due to quantum effects near the event horizon. This radiation, which comes from the quantum fluctuations of particles and antiparticles, suggests that black holes may eventually lose their mass and evaporate. This evaporation process has led to speculation about what might remain after a black hole has disappeared. Could there be remnants of the matter that once fell into the black hole? Is it possible that the information contained in these objects could somehow escape the event horizon? Some physicists argue that this information is not lost, but encoded in the radiation itself. Others suggest that the collapse of a black hole could open a gateway to a new universe, one born from the very matter that fell into the black hole. This notion is often linked to the theory of the multiverse, which proposes that our universe is one of many, potentially with different laws of physics and initial conditions. One of the most intriguing possibilities related to the universe beyond the event horizon is the concept of baby universes. According to certain interpretations of quantum mechanics and black hole thermodynamics, when a black hole collapses, it could give rise to a new universe. This new universe would be created in the aftermath of the collapse, inheriting certain properties from the black hole, but also evolving on its own. This idea is supported by the quantum bounce theory, which suggests that the singularity is avoided through a quantum mechanical process that causes the collapsing matter to bounce instead of collapsing to infinite density. If this theory holds true, each black hole could act as a seed for the formation of a new universe, effectively creating an endless cycle of cosmic rebirth. The multiverse hypothesis also ties into this idea, suggesting that black holes could serve as gateways to different dimensions or universes. If our universe were inside a black hole, then the multiverse would be a collection of universes, each created by its own black hole. These universes would be completely isolated from one another, separated by the event horizons that mark the boundary between different cosmic realms. It's a captivating thought. We may be living within a black hole, and every black hole could contain an entire universe of its own, hidden from us by the one-way nature of the event horizon. While this idea is fascinating, it is still highly speculative. There are many challenges to proving such theories, particularly when it comes to observing the inside of a black hole. Since no light can escape the event horizon, direct observation is impossible. But indirect evidence might exist. For example, the way galaxies spin, the cosmic microwave background radiation, and the distribution of large-scale structures could all be influenced by the presence of black holes and their internal properties. As scientists continue to probe the mysteries of black holes, the question of what lies beyond the event horizon remains a central topic. Whether it's the birth of new universes, the preservation of information, or the existence of alternate dimensions, the universe beyond the event horizon may hold answers to some of the most profound questions in cosmology. While we may never be able to directly observe this mysterious realm, our growing understanding of black holes and the nature of space-time might one day reveal the secrets of what lies beyond. As we conclude this chapter, we are reminded that the universe is far stranger than we could have ever imagined. The possibility that our universe could exist inside a black hole and that every black hole contains a new, unique cosmos is a mind-boggling thought. Whether or not this theory is true, the universe's mysteries continue to unfold, challenging our understanding of space, time, and reality itself. The event horizon may be a boundary that we can never cross, but the knowledge and curiosity that fuel our exploration of these enigmatic regions may ultimately bring us closer to the truths that lie beyond. Chapter 22. The Role of Hawking Radiation in Understanding Black Holes. Black holes, once thought to be perfectly black and devoid of any radiation, have recently become the center of one of the most fascinating discoveries in modern physics. Hawking radiation. Proposed by physicist Stephen Hawking in 1974, this radiation, which emerges from the event horizon of black holes, presents a paradox that challenges our traditional understanding of these cosmic giants. Hawking radiation arises from quantum mechanics, the field of physics that governs the behavior of particles on the smaller scales. According to quantum theory, even a vacuum is not truly empty. Instead, it is filled with virtual particles that constantly pop into existence and then annihilate each other. These particles are pairs, one with positive energy and the other with negative energy, and they appear for brief moments before disappearing again. However, near a black hole's event horizon, things get more complicated. Hawking's theory suggests that when these virtual particle pairs are created close to the event horizon, one of the particles may fall into the black hole while the other escapes into space. The particle that escapes is what we now recognize as Hawking radiation. The key to understanding this is the difference between the positive energy particle, which escapes, and the negative energy particle, which is drawn into the black hole. The negative energy particle, being absorbed by the black hole, effectively reduces its mass. This process leads to what's known as black hole evaporation. Over time, as more and more particles are emitted as Hawking radiation, the black hole loses mass. The more radiation a black hole emits, the faster it loses mass, eventually leading to its disappearance. This presents a remarkable paradox because it implies that black holes are not truly black at all. Instead, they radiate energy, which leads to their gradual evaporation. The idea of a black hole disappearing through radiation challenges the classical view that once something crosses the event horizon, it is lost forever. Yet Hawking radiation does more than just offer a new understanding of black holes. It also introduces a profound issue for physicists: the loss of information. According to the laws of quantum mechanics, information about a physical system cannot be destroyed. If a black hole evaporates and disappears, what happens to the information that fell into it? This is known as the information paradox, and it remains one of the most debated questions in theoretical physics. Hawking himself originally suggested that the information might be lost forever, which conflicted with the principles of quantum theory. Later, he revised his position, proposing that the information might be encoded in the Hawking radiation itself, though how exactly this would happen remains unclear. The paradox highlights a fundamental conflict between general relativity, which governs the behavior of large objects like black holes, and quantum mechanics, which governs the smallest scales of the universe. Hawking radiation also offers a unique window into understanding the nature of black holes, without having to observe them directly. Although no one has yet detected Hawking radiation from a black hole, since the radiation is incredibly weak and difficult to measure, it offers a theoretical framework for studying the properties of black holes. In fact, the idea of black hole evaporation leads to the speculation that all black holes, regardless of their size, will eventually shrink and vanish. This has significant implications for the ultimate fate of the universe and the long-term evolution of the cosmos. But while the concept of Hawking radiation challenges our understanding, it also opens new possibilities for the study of black holes. It suggests that black holes may not be eternal, as once believed, and their eventual demise could provide valuable insights into the nature of spacetime, gravity, and the quantum realm. The study of black holes, and particularly the role of Hawking radiation, could help physicists bridge the gap between the two pillars of modern physics, general relativity and quantum mechanics. The implications of Hawking radiation extend far beyond black holes. They touch on the fundamental nature of space, time, and the universe itself. For instance, the discovery that black holes could eventually evaporate suggests that the universe itself might also undergo a form of evaporation, a process that could lead to its eventual heat death. This long-term cosmic fate raises questions about the origin of the universe, the nature of dark energy, and whether the laws of physics as we know them are the final word on the universe's behavior. Despite the profound consequences of Hawking's discovery, much of the science surrounding Hawking radiation remains theoretical. No direct evidence has yet been found to confirm its existence, and detecting it remains one of the most difficult challenges in astrophysics. Nevertheless, the search continues, as the implications of such a discovery would fundamentally change our understanding of black holes, space-time, and even the very nature of reality itself. In the end, Hawking radiation represents both a promise and a paradox. It promises to unlock the mysteries of black holes, providing a new way to observe their behavior from the outside, but it also deepens the mystery of the black hole information paradox. How can we reconcile the notion that information can be lost in a black hole with the laws of quantum mechanics? While the answer remains elusive, the pursuit of understanding continues, pushing the boundaries of what we know about the universe and our place within it. Chapter 23. Black Hole. Imaging, the challenge of seeing the invisible. Black holes, by their very nature, are invisible. Their defining feature, the event horizon, is a point beyond which not even light can escape. This makes observing them directly an enormous challenge for astronomers and physicists alike. However, the advent of cutting-edge technology, particularly the Event Horizon Telescope, EHT, has opened a new frontier in our understanding of these cosmic objects. The primary issue with black hole observation is that their immense gravitational pull distorts space-time so much that light cannot escape. When we look at the night sky, the stars, galaxies, and other celestial objects we see are all emitting light that travels through space. This light, or electromagnetic radiation, is the only way we have to observe distant objects. Black holes, however, absorb all light that crosses their event horizon, making them essentially invisible against the backdrop of space. We can't see a black hole with a telescope in the traditional sense, so how do we know they exist at all? While black holes themselves remain invisible, the regions surrounding them can give us clues to their presence. The material that gets pulled toward a black hole, particularly in the case of supermassive black holes at the centers of galaxies, can emit intense radiation as it is heated up to extreme temperatures while spiraling into the black hole. This process creates a luminous disk of gas and dust known as an accretion disk. As material gets compressed and accelerated, it emits radiation in the form of X-rays, radio waves, and other wavelengths that can be detected by telescopes. The EHT, an array of radio telescopes around the world, made a breakthrough in 2019 by producing the first ever image of a black hole's shadow. The black hole in question, located at the center of the galaxy M87, is a supermassive black hole with a mass 6.5 billion times that of the Sun. By observing the light surrounding the black hole and analyzing the way the black hole bends light, the EHT team was able to create an image that showed the shadow of the event horizon, surrounded by the glowing hot gas of the accretion disk. This image was a monumental achievement, marking the first time humanity had ever captured an image of a black hole, despite the fact that we cannot directly observe the object itself. The shadow itself is a result of the intense gravitational pull of the black hole bending light around it, creating a dark, circular region at the center of the glowing accretion disk. The EHT team's work opened up the possibility of studying black holes in a way that had been previously unimaginable. However, imaging a black hole is not as simple as pointing a telescope and capturing a snapshot. The immense distance to black holes, the warping of space-time around them, and the limitations of current technology all pose significant obstacles. The light emitted by the accretion disk is faint, especially when it is billions of light years away. The EHT relies on a technique known as Very Long Baseline Interferometry, VLBI, which involves linking radio telescopes across vast distances to create a sort of virtual Earth-sized telescope. This technique allows astronomers to achieve the resolution necessary to see the fine details of black holes. But even this method requires years of planning and coordination. In addition to the challenges of capturing clear images, interpreting black hole images is also a complex task. The gravitational effects near a black hole are so extreme that they cause light to bend and warp in unpredictable ways. This phenomenon, known as gravitational lensing, means that the image of a black hole's shadow is distorted by the strong gravity surrounding it. For example, the accretion disk may appear to be warped or stretched as light bends around the black hole's event horizon. Sorting through these distortions requires sophisticated mathematical models and simulations to reconstruct an accurate image of the black hole. Scientists must account for the many variables in play, such as the movement of gas, the nature of the black hole's spin, and the gravitational lensing effects. The challenges of imaging black holes also extend beyond the black hole itself. The process of studying the material surrounding a black hole, especially in the case of supermassive black holes at the centers of galaxies, involves looking at the behavior of gas and radiation under extreme conditions. How matter behaves in the strong gravitational field of a black hole is still a major area of research in astrophysics. Understanding these processes will shed light not only on black holes, but also on the fundamental laws of physics, such as general relativity and quantum mechanics. The future of black hole imaging is promising, with new advancements on the horizon. For instance, the next generation of telescopes, such as the Square Kilometre Array, SKA, and the James Webb Space Telescope, will provide even more detailed data on the region surrounding black holes. Additionally, future upgrades to the EHT are expected to improve the resolution of black hole images, allowing scientists to capture more detailed views of these enigmatic objects. There are also plans to use gravitational waves to study black holes, which would provide another way to observe their behavior without relying on traditional electromagnetic radiation. The ongoing quest to see, understand, and explore black holes will continue to push the boundaries of technology and physics. In conclusion, while imaging a black hole is one of the most difficult challenges in modern astronomy, recent advances in technology have made it possible to observe and study these cosmic objects in ways that were previously thought impossible. The first image of a black hole's shadow is just the beginning. As our tools and techniques continue to improve, we will undoubtedly learn more about black holes and their role in the universe. These observations will not only expand our understanding of the most extreme objects in the cosmos, but also help us uncover the mysteries of space-time itself. Chapter 24: The Ultimate Fate of the Universe. The fate of the universe, a question that has captivated the minds of scientists and philosophers for centuries, is intricately tied to the nature of black holes. These cosmic giants not only shape the lives of stars and galaxies, but also control the long-term destiny of the universe itself. In this chapter, we'll explore the ultimate fate of the universe, focusing on black holes' role in the process, as well as the profound implications of their eventual decay through Hawking radiation. The universe is in constant motion, expanding and evolving over time. This expansion, driven by dark energy, is causing galaxies to drift further apart at an accelerating rate. For billions of years, this expansion has been at the heart of cosmology. However, as we look further into the distant future, the fate of the universe becomes increasingly uncertain. Will the universe continue expanding forever, growing colder and more desolate? Or will it eventually collapse in on itself in a cosmic reversal known as the Big Crunch? A key factor in determining the universe's long-term fate lies in the study of black holes. These objects, formed from the collapse of massive stars, possess such immense gravitational pull that they warp the very fabric of space-time. The largest black holes, known as supermassive black holes, reside at the centers of galaxies, including our own Milky Way. While these objects are fascinating, their long-term effect on the universe's destiny is even more significant. Over time, as galaxies continue to merge and collide, supermassive black holes will become increasingly isolated, surrounded by an ever-thinning cosmic landscape. This isolation will result in a significant change, the gradual evaporation of the black holes themselves, a process driven by the phenomenon known as Hawking radiation. Proposed by the theoretical physicist Stephen Hawking in 1974, Hawking radiation suggests that black holes slowly lose mass over time due to the quantum effects at their event horizons. This radiation is a direct consequence of quantum fluctuations near the event horizon, where pairs of particles and antiparticles spontaneously form and annihilate. Occasionally, one of these particles escapes the black hole's grasp, while the other is drawn back into the singularity. As this process continues, the black hole loses mass and energy, ultimately leading to its eventual evaporation. For smaller black holes, this process happens relatively quickly. Stellar mass black holes, formed from the collapse of individual stars, can take millions to billions of years to evaporate fully. However, the supermassive black holes at the centers of galaxies, massive objects with millions or even billions of times the mass of our Sun, are far more enduring. These black holes can take on the order of 10 to the power of 100 years to evaporate completely, a timescale that far exceeds the current age of the universe. As these supermassive black holes slowly shrink, they will continue to emit Hawking radiation, causing them to lose mass and energy at a decreasing rate. Eventually, the remaining mass of the black hole will reach a critical point where it can no longer sustain its own gravitational pull. At this moment, the black hole will collapse into a singularity, and all of the information it has absorbed, everything from stars, planets, and galaxies to light itself, will be lost to the fabric of space-time. However, the ultimate fate of the universe may not be as simple as the slow decay of black holes. There is an alternative possibility known as the Big Rip. The Big Rip is a scenario in which the universe's expansion continues to accelerate, eventually tearing apart galaxies, stars, planets, and even atoms themselves. This fate is tied to the properties of dark energy, the mysterious force that is causing the accelerated expansion. If the strength of dark energy continues to increase over time, it could eventually overcome the gravitational forces that bind galaxies and stars together, causing them to be ripped apart in a violent end. While the Big Rip is still a speculative hypothesis, its potential implications are staggering. As the universe continues to evolve, the process of cosmic expansion will likely accelerate, and the universe will grow increasingly cold and desolate. Stars will burn out, galaxies will drift farther apart, and matter will become increasingly diffuse. In this scenario, black holes will remain the last vestiges of the universe's once energetic state, quietly evaporating over trillions of years until they are no more. Interestingly, the eventual end of black holes may provide some insight into the fate of the universe itself. Hawking radiation, as it reduces the mass of black holes, may also alter the structure of space-time in unexpected ways. If the process continues, it could lead to the formation of a new cosmic state, one where the laws of physics as we know them break down. This scenario, known as the heat death of the universe, suggests that the universe will eventually reach a state of maximum entropy, where no usable energy remains, and all matter is spread thinly across an ever-expanding space. In this state, the universe would be in a state of irreversible decline, and no new stars or galaxies would form. The process of cosmic evolution would come to a halt, and the universe would become a cold, dark, and lifeless place, slowly fading into nothingness. This scenario suggests that the universe's ultimate fate is to experience a long, slow death, with black holes and cosmic remnants marking the final chapter in the story of existence. However, the implications of Hawking radiation and the eventual decay of black holes raise an important philosophical question. Is the end of the universe inevitable? While the physics of black holes and cosmology suggest that the universe may eventually succumb to entropy, some have suggested that there may be ways for consciousness and complexity to transcend these limitations. Perhaps in the distant future, advanced civilizations may find ways to manipulate the laws of physics or even escape the boundaries of the universe itself. For now, though, we are left with the sobering reality that the fate of the universe is inextricably tied to the behavior of black holes. As these cosmic giants slowly evaporate and the universe winds down, the possibility of new forms of life and consciousness arising seems remote. Nevertheless, the story of the universe's end is not one of finality, but of transformation. Just as black holes serve as a gateway to new universes, the end of our own universe could be seen as the beginning of a new chapter in the ongoing cycle of cosmic rebirth. In conclusion, the fate of the universe remains one of the most profound questions in modern science. The process of cosmic evolution, marked by the slow decay of black holes and the eventual entropic death of the universe, provides a humbling reminder of the limits of our understanding and the inevitable passage of time. Yet as we look toward the far future, there is always the possibility of new discoveries and new paradigms that might reshape our understanding of the cosmos and its ultimate destiny. Chapter 25. The limitations of human knowledge and space exploration. As we conclude our exploration of black holes, the question inevitably arises, where does humanity go from here? We have delved into the complexity of these cosmic giants, their role in shaping the universe, and the boundaries they impose on our understanding of space, time, and the very fabric of reality itself. But as much as we may strive to understand black holes and the universe, we are continually reminded of the inherent limitations that come with our human perspective and capabilities. The boundaries of human knowledge are not defined by the lack of ambition or intelligence, but by the very nature of the universe itself. The vastness of space, the extreme conditions at the heart of black holes, and the constraints of physics present insurmountable challenges to space exploration. It is not that we are incapable of making incredible strides in our quest for understanding. Rather, it is the universe that imposes its own set of rules, rules that sometimes seem beyond our grasp. Human exploration of space has advanced tremendously over the past few decades. We have sent probes to the far reaches of our solar system, explored distant moons and planets, and even glimpsed the edges of our observable universe. Yet as we stand on the precipice of further discoveries, we realize that the true mysteries of the cosmos, particularly those surrounding black holes, are still far beyond our reach. One of the most profound limitations lies in the sheer scale of space itself. The distances between celestial bodies, galaxies, and black holes are so vast that they defy human comprehension. For example, even with the fastest spacecraft we have ever built, like NASA's Parker Solar Probe, traveling to a black hole would take tens of thousands of years. The challenge is not just technological, it is also existential. How can we even begin to approach something that is so far beyond our lifetime, or the lifetimes of many generations to come? How can we plan missions that will span the duration of time itself? Moreover, the energy requirements for such an endeavour are staggering. As we've discussed, the immense distances combined with the need for propulsion systems capable of sustaining such long journeys create an insurmountable barrier. Current technology simply does not have the power to propel a spacecraft anywhere near the necessary speeds to travel to distant black holes. Even with advancements in propulsion theory, such as laser propulsion or antimatter engines, the energy demands remain far beyond our current or foreseeable capabilities. But the limitations go beyond technology. Theoretical physicists have long debated the nature of black holes and what lies inside them. But we are limited by the fact that we cannot directly observe or interact with these objects. The event horizon, that fateful boundary where not even light can escape, is a one-way wall. Information and matter can fall in, but they cannot return. This creates an insurmountable barrier for any observer hoping to study black holes firsthand. All we can do is observe their effects on the surrounding space and infer their properties based on indirect evidence. Additionally, the question of whether we can ever truly reach a black hole remains an open one. The sheer physicality of what it would mean to approach or even enter one, a singularity at the center of space-time where physics breaks down, challenges our basic understanding of reality. What happens to the laws of physics when we get closer to the event horizon? What happens to time and space itself? While we have theories and equations that can model these extreme conditions, we cannot test them firsthand. The nature of black holes, both physically and conceptually, seems to exist beyond the realm of human exploration. Furthermore, there is an undeniable philosophical question embedded in our quest for space exploration. Why do we pursue these challenges? What drives us to explore the infinite unknown, despite knowing that we may never reach the answers? Perhaps it is the inherent curiosity of human nature that compels us to push boundaries and seek answers to questions that may never be fully understood in our lifetime. But this quest for knowledge is also a reflection of our need to understand our place in the universe and ultimately to transcend the limitations of our own existence. In the face of such monumental challenges, we are often left to wonder, is it possible to reach a black hole? Can we truly explore the farthest corners of the cosmos and unlock its deepest secrets? While the technology of today may not provide the tools we need to reach black holes, it is important to remember that science and human exploration are not bound by a single generation or time frame. The future of space exploration lies in the hands of those who come after us. The questions we ask today may be answered by future civilizations, equipped with technology and knowledge that we cannot yet imagine. In conclusion, our journey into the mysteries of black holes has brought us face to face with the limits of human knowledge and exploration. While we may never fully reach or understand the black holes themselves, our quest for knowledge is far from over. The challenges we face today are merely stepping stones for future discoveries. Just as the stars are distant yet beckon us with their light, so too do the black holes represent the ultimate frontier, an enigma that may one day be unlocked by future generations who will carry forward our legacy of curiosity and wonder. Until then, we remain on the threshold of the unknown, gazing into the vastness of space with awe and reverence, knowing that the pursuit of knowledge is an endless journey.